I think it's fine. I think it's expect like they're like on the edge. Hey, testing, ladies and gentlemen, live in 2 minutes. Hello, good morning, welcome. In the words of one of my favorite attendees, welcome to the planetarium. I think it's an appropriate word because the Bitcoin developer world, Bitcoin++, the scripting edition conference with established tradition. Blessed to be here, everyone. Pass over to Nifty. I'm just here for transition.
Texas, but the 6th ever talking about Bitcoin script. For being our headline sponsor, Human Rights Foundation. Human Rights Foundation has been really great in terms of go over and check what's going on Twitter every once in a while, or Nostr, if you're that kind of decentralized maxi. And it's rare to really spend time talking to each other face to face. You know, we live in a world that's very connected. It makes you think that you're able to get to know people. Really cool and special that all, you know, I think there's a lot of interesting things going on in computing across the ecosystem, not just in Bitcoin. There's really cool stuff going on in like what we call AI as well. And I think we've got some of the coolest and most interesting projects. So that's really exciting. Part of these discussions, I think that we're going to have in person, we're going to go back into some history. What does it mean to add covenants? Jeremy Rubin, I think, really kicked the skills and new projects and people that have kind of been continuing on in that sort of thread of stuff, along with new projects like the topics we get into. I also think it's worthwhile pointing out that, you know, over the last few years, Bitcoin has brought in a lot of news with new people trying out things, maybe some new people and new parts of the community, while also really digging into what makes tiers, all these new people being in the same rooms that I think means we come with different ideas. Is a lot of this conflict tends to happen at the level of the protocol. And I think the place that you see conflict is what is in the protocol for us as a community and a protocol. Thanks again, everyone, for coming. Barbecue. Well, thank you so much for coming. Running a little bit behind. I'm trying to think if there's any like last minute social media without blacking out everyone's face and personal information. I think that's pretty much for people to maintain their anonymity. Great. Okay. I think without much further ado, I'd like to welcome to the stage our MC, who's going to introduce our.
Bitcoin++ is probably where you come each year and you start to feel like maybe you're getting a little bit rusty.
That was an introduction. Thank you. I will switch. Okay, so for future reference. That's better? Oh, wow, I'm loud now. Legal? Sure. Okay. Okay, now let's see what happens when I hit this button. Fantastic. Okay, good morning, everybody. Morning, thank you. Very good, there's always one. Now, who here is familiar with Bitcoin script? Put your hand up, please. Okay. Christian is lying, thank you. Okay, right, now, okay. Okay, I wrote this whole thing assuming that everyone knew Bitcoin script, and then I went, oh, maybe they don't. So, in 12 seconds, a simple stack-based language, every Bitcoin output has one attached. You give it a pile of stack elements, and then it's a little program. It contains opcodes to push things onto the stack, push things off the stack, add numbers, etc., right? You feed this program stack element. Gives you the thumbs down. your transaction doesn't work, right? The most common script is simply to check a signature provided on the stack matches the transaction that we're spending. Okay, any questions? Good. Okay, perhaps we're down to 35 minutes. I would like to take you on a journey. If you don't want to go, that's cool. I suggest you just nap because the next 4 days look to be pretty intense. But if you do travel with me, it's going to be a bit different, okay? I have the world's most boring slides. I didn't even use Midjourney once, right? Instead, I have some of the descriptions that I might have used to prompt images, but I'm cutting out the middleman and feeding them straight into your imagination, okay? So let's begin. One of the original opcodes, Bitcoin opcodes, was disabled in version 0.3.1 in 2010. There's the CVE number, okay. It's recently been reproposed by many people, including Ethan Heilman, but with a 520 byte restriction. Now this opcat, so it can't produce them, you're consistent, but it does feel limiting, right? The obvious problem with this is that if you don't restrict it, right, you end up with the obvious problem here by having a total stack limit. You were allowed to have 1,520 byte stack elements, so let's just say you can have up to 1,000. But then you hit another problem. Let's look at this little script here. Op-dup, op-SHA-256, op-drop. If you have 4 megabytes worth of this, you're basically duplicating the top entry, hashing it, and then throwing it away again and again and again. So while we've solved the memory problem with a total stack limit, that leaves this problem. So if is what happens if you have a 4 meg script that does this with 520 byte. You can't even see a bump image on the right, and you can see a full block of those takes 700 odd seconds. This is what we call in engineering bad. Now, better maybe, which is that check sig operations are slow. And Taproot solves this with a SIGOPS budget. You know, you're doing something weird. So, obvious question, can we do the same thing with a hashing budget? The TapScript SIGOPS budget works because it's generous enough that you don't have to worry about it, but low enough that it prevents you from DOSing the network. Can we do the same thing here? Okay, well, this is the question. Let me show you another little script. Opt-up, and actually, it's still pretty bad. There's no hashing in here anywhere. Okay, so it turns out that it is not just hashing. On modern CPUs, SHA-256 just isn't that slow. It's also hyper-optimized in Bitcoin because we use it everywhere. Actually touched by a reasonable implementation. Okay, so the budget cost should depend on the size. This leads us to what I call a VAROps cost model, right? It turns out all our, and that's sensible because that's how modern machines work. It's how caching works, right? If you cache something, your cache loves you when you access it nice and linearly, and all of them do that. We can basically assume that that cost dominates, right? We don't care about actually resizing the stack itself. We don't really care about whether you're doing a read or a write or modify. That's all good. We assume that we're using simple arrays and vectors, which we do currently. And we assume that anything you're doing with the things in your CPU is basically free, except for hashing. Okay. And this is important. You have to think about the worst case. How bad can it get? How much access is this 0 if it is fail? Okay, 0, 0, 0, 0, 1, right? It might have to go 520K to find whether it's 0 or not. So the cost is simply the length. Straightforward. 520K of reads. Opt-up, a little bit different. You make a copy. Read, write, read, write, read, write. Operand length times 2. Okay, so far our model looks good. Let's look at op equal. This one's a little bit weird. It's either free, because if the lengths are unequal, you don't even need to look at them. You go, they're not equal, I know that. Or it's the length, which is both of them, times 2. So the cost isn't actually a linear function necessarily of your sizes. We can do this for every push opcode. For push, you're kind of copying out of your data stream. So you can technically pay the cost to write it on the stack. Okay, that's fine. Everything else, you know, how much data did you copy? Twice that is your number. Okay, this is good. verify again, equal verify, ifed up. You should note that there's no var ops table for op if and op not if, and that's one. You're not allowed, doesn't have that. Okay. Now, hashing. We talked about hashing. And for that, it's length times by some hash factor, right? So, because hashing is one of those cases where our assumption doesn't hold. You do actually spend some CPU churning through the data, so you can't just go memory bound. And we see here this hash 256, which is hashing it twice. We don't care. That's an edge condition, right? We care about really big data, in which case doing one extra hashing is in the noise. Okay. And there are two old hash opcodes, RIPEMD 160 and SHA-1. Nobody's going to optimize those. I don't want them to have to do it. So you just fail. If that's too big, you fail. And you start to question your life choices if you ever hit that condition. Because why are you doing that? Okay, now the hash factor I mentioned is to be derived later. And we'll see that in a later slide. Okay. So we have our model. And this constrains our worst case behavior. So let's restore some opcodes now, okay? Let's start with the bitwise ones. Op invert flips every bit. Well, the cost is obviously the length, that's easy. Op and is the sum of the two lengths, whereas op XOR is the double the minimum of the shortest one. With OR and XOR, you presume that you're operating into your longer one, right? You're flipping the bits. You XOR, and then if you run out of the short one, you just stop. With AND, you've got to zero out everything else. So AND is the sum of the two, and OR and XOR are slightly cheaper. Okay, cool. Now opcat itself, remember where we started with me getting upset about opcat being limited? Well, let's look at it. If it simply allocates a new vector and copies them both in, it looks like this. The cost is obviously copying both of them, twice the input length sum. But that is not how you implement opcat, right? Any programmer will tell you what you actually do is you resize in place and then copy, because you're hoping the resize in place is basically free. But that turns out to be the same cost. And the reason is, in the worst case, that reallocate in place will have to do a copy internally anyway. So it's the same number, right? Remember, you're always allowed to beat the model. You can do smart things in certain cases and completely outstrip the model. That is fantastic. You're doing really well. Faster is always better. But you can't make the worst case worse. Okay. Let's do the other string opcodes while we're here. Left and right. Left is easy. It's basically free. You do have to read the offset. Don't forget that the number of bits that you're supposed to, or number of bytes you're supposed to cut at, that could be 520K long, right? Because it just could have a whole heap of zeros in it. So you do have to read that. But once you've done that, you just chop. You don't touch any data at all. Right is a bit different. You have to move the data down to the front. By the way, left and right do exactly what you expect. They cut at certain points. You take the left part, or you take the right part. Okay, so right's a bit weird. You take the length, minus however much you said, whatever offset you said, and that's the amount. Technically, that's bottom to zero, but you'll figure that out. Substring is basically they tell how much to copy out of the middle. The cost is effectively the amount that they tell you to copy. Great, okay. Now we're going to get to two of my least favorite opcodes. L shift shifts a value to the right, and R shift shifts a value to the left. Thank you, little endian. Okay, so I have renamed these to upshift and downshift so we sound vaguely coherent, okay? Downshift has to just move some bits from the end to the start. So it's pretty straightforward. You basically go, how many bytes are you actually moving? You've got to read the value. You've got to figure out how much you're moving. That's fine. Upshift, however, upshift has two distinct cases. And I'm still going back and forth whether we should split these, but you're either moving a whole number of bytes, which is easy. It's basically just a mem move, which is basically you allocate and you just shove stuff into the front. Or you have to allocate, shove stuff into the front, and then add one byte at the end and shift everything along, which means another pass through. So it's 4 times the value. So that's kind of ugly, and the names are terrible. Now, unlike the L shift and R shift, which was in 0.3.0, these versions do trim the trailing zeros, because trailing in Little Endian means the big ones, right? So instead of 00001, you know, it's just 1. We don't do that, because that's an interesting design choice for shifting. Okay, okay. That did get ugly for a moment, but we're through. We have unshackled our stack limits. We've restored our opcodes. What else is there to do? Well, script is limited to signed 31-bit arithmetic. But we can have up to 51 bits of Satoshis, right? I can't, but in theory, someone can. Actually, I'm quite happy with 31 bits of Satoshis if anyone wants to help me test. And there are also other unsigned 32-bit fields that we'd like to deal with, right? Now, Blockstream's Elements has a whole suite of opcodes to do this, right? It has these 64-bit opcodes. It has conversions back and forth between the 31-bit script numbers we have today and those. And every time, when you add or subtract values on the stack, you get 2 values. You get the value and a flag that says whether it succeeded or not, whether it overflowed, right? Now, this approach makes me a little bit skeptical. Firstly, because it's ugly. You end up basically doing op verify after every single arithmetic operation. But also because my first computer was 8-bit. Well, it was kind of like, it had pretensions of being 16-bit, but really it was 8-bit in 16-bit pants. And then I went through a 32-bit transition, and then I went through a 64-bit transition. So I just have a feeling that I cannot guarantee you that 64 bits will be enough forever. And at this point, I'm looking at my varops hammer and going, what if add simply doesn't overflow? Right? What if we just go, well, variable length integers, right? Now, one of the problems with variable length integers is where do you put the sign bit? And the answer is don't. Everything is unsigned. And we should define all our arithmetic ops to normalize, to truncate unnecessary zeros. If we do this, we end up with something that looks like this. Here's how much everything costs. Op negate and op abs are unused. There doesn't even make any sense anymore. We don't have signed things. So potentially 2 more op success opcodes. But every other comparison is pretty much exactly what you'd expect, right? This is straightforward. Okay, well, that's cool. Subtraction is fun. We have no negative numbers, so it can fail. And I thought about doing this element style push the success flag, but I know you're just going to do op verify after it every single time. So let's just do that directly. You're not allowed to underflow. It fails. If you really want to do that, do your comparison first, check, but you don't. It's fairly straightforward. It's the sum of the 2 lengths. You're basically subtracting everything. Worst case, you subtract something and you have to go all the way through because it underflows all the way through. But that's OK. This does assume that you subtract in place, by the way. You're not subtracting to a third thing because that's 3 passes, not 2. But that's fine. Yep. Now, but we do define it to normalize. Remember I said we might as well trim zeros. Arithmetic ops should trim zeros. That just makes perfect sense. We do that today. But you can't do it in the naive way. You can't do the subtraction and then walk back through it to find how many zeros are and chop it off. Because that would be a 3rd pass. And the model doesn't allow that. You're only allowed 2. But that's easy. What you do is you just track the zeros as you go. If you put a 0 there last, you remember, and then you go, OK, that's fine. Add. Can we add? Yes. Well, it's just like subtract, except it can overflow. And if it overflows, worst case, you have to add a byte, which means you have to reallocate the whole thing, which means another copy, which costs you twice the length. So worst case, it's basically 4 times. So it's twice as slow as add. But it works in the model. OK. Here's implement this, right? Partially to test the model, but also to get a feel for what's performance like. You know, I've used 520 kilobyte opcodes, operands, which I know I said that. Here is the implementation. Now this matters, right? The blue one on the left, the columns on the left, are the naive, byte by byte, as possible implementation. Blind, that kind of cream-colored column, that is what the SHA-256, remember our SHA-256 friend? That, and turns out that's about 8 times as expensive as doing an invert. We've done that. Let's bring back some other opcodes. Opmul, let's multiply. It's basically a series of adds, right? Now, at this point, you have a 64-bit multiply. Even ARM, even Raspberry Pis, now have a 64-bit run Bitcoin on reasonably today. Can handle 64-bit multiplies, so that's easy. You do that. Tom Cook, there's FFTs, there's the whole, and that is wonderful for them. I looked at libGMP, it is so fast. It's unbelievably fast. But it has about 8 to 12 different multiplication routines. I have not done opdivide. It's kind of the final boss of variable length arithmetic, and it is on my to-do. I have. They will stay tuned to free us from the shackles of small size limits, right? But we didn't actually discuss how much budget do I get? How much budget do I start with? That is actually not a trivial question to answer. But how long does that take? Well, on my laptop, it takes 4.92 seconds. And during that time, I could do about, what, 35 gig of op inverts. And so therefore, for that multiplication factor, for every byte, you will get 8,825 VAROPS budget to play with. But when you think about it, and you could use up your entire VAROPS budget and waste that much time as well, again, doubling your block validation time, right? So really, it makes sense to combine this into one budget again and go, well, whatever you get for 50 bytes, you can do a check sig, and will come out of the same budget. If we have introspection opcodes, okay, if we have more advanced introspection opcodes, certainly, then the budget should be per transaction, because a script can ask about the action size, not your individual witness weight, which, how would we transition? And I had to redo this slide yesterday because we had a discussion about this, and everyone hated the way I transitioned. I added a new SegWit version, BT1Z, but everyone went, you don't need to do that, because they want the parity bit back, because apparently it just makes life really hard to do 32-byte X-only pub keys. So if they did that, we could say, okay, in that case, you're using a new script. Because we want to reuse existing opcodes and change the number semantics, it would be awkward just to add a crap load of new opcodes, add V, add sub V, sub 1V, all those. If we want to change opcode semantics, we really do need to update the script version to be TapScript v2, internally at least. But we also want to avoid this dummy key penalty, right? So if you use Taproot today and you only want a script, you put in a dummy pub key. And that seemed like a good idea at the time. You use Taproot, and there's no particularly good reason for that. So it would be nice to, you either have a raw Merkle sum in there, or you use a dummy nums point. It also, frankly, makes writing the script interpreter a lot clearer. At this point in our journey, we have climbed mountains, you know, crossed rivers, battled dragons, well, cats. We battled cats. They've got claws. That's like a, okay, imagination. We have battled dragons. Let's stick with that. We seem to have a way to place reasonable limits on the 51 opcodes that deal with variable length stuff in script. Many of the restored ones in a way that doesn't actually seem too onerous, right? It's pretty compatible with stuff that we do already. So at this point, I want to look briefly into the future. Okay. There we go. Why did I not just break this up? Okay. It's worth noting, opcat by itself, and certainly the other opcodes, give us covenants badly, right? Right? We've got them badly. And now we can handle values nicely. We can actually deal with 64-bit values in the same way and everything else. It seems obvious that let's just give ourselves direct introspection. Let's just ask, what is the value of this? But like kind of a thought experiment on why you can't just live with called op check sig. Or to give it its scientific name, op select TX parts from flags, SHA-256, and check sig, right? Now imagine you're like a VAROPS maximalist, and you're like, you know what? Check sig from stack. It's the stupidest name ever. Of course, it's from stack. We're a stack machine. Everything's from stack. But you know, just to differentiate from, it could have containing this script, about 38,000. The cost model of that is about 30 times the budget that we have. Right. Obviously, you can see from this that that is grossly inefficient and exceeds our budget, even though our budget is incredibly generous, right? Which is another way of saying the same thing. It's too slow. And it's stupid. They're all doing exactly the same hash that has been calculated once for the entire transaction and things like that. We need this to make this work. You can't just use var ops. Okay. Now, Bitcoin has changed a bit since 2010, you may have noticed. But two things particularly stand out. We've added taproot trees and we've added ops success. Ops success is fantastic because it's mere presence in a script. Just being there makes the script succeed. And taproot trees allows you to specify a number of conditions and meet only one of them. Fantastic. But this presents a problem for introspection. You see, if you want to say, this script, I don't care what it does, but it has to test condition X. It has to be a 20-block delay or whatever else, and then whatever else you want. You can't do this. You see, you can't use separate taproot leaves because they provide an or. You want an and. You want to say this condition and something else. And you can't do the obvious thing and go, well, as long as your script starts with 16 op CLTV, then I'm happy, because they can stick an op success later on, and the whole thing will succeed without running that at all. So one way of solving this is to produce something like an opcode like op segment. It does exactly what it sounds. You scan the script, you divide it up along the op segment divisors, and you effectively prevents an op success and condition, say the script must do. Because of the way taproot trees work, you do an operation where you take a key and you tweak it. It's actually surprisingly slow. And because taproot trees are sorted lexicographically, that turns out to be exactly there. The best way I can think of to do that is have a byte reverse. And of course, while you're here, let's get op check sig from stack. I want to call op check does deconstruct stripped a little bit. Okay. Now let's go further in the future. What else could we want? If we want script to be this grown-up cat that you input and op h output. You want to be able it pushes the input number on the stack, runs up until the next op end if. You can pre-process this, right? You can say, oh, I can expand this out. Because at the time you're looking at the script, you know how many inputs and outputs there are. So you can actually just expand it out into a bigger script that has this cut and paste over and over again. It does mean weirdly that the weight of the script now depends on the number of inputs and outputs. Because even the mental model of this existing proves to be useful. So even if we never actually implement op h input and op h output, they turn out to be very powerful tools to evaluate other things, and we'll see that in a moment. Okay, now, that was actually a controversial statement a number of years ago, but no, and it has side effects on a scheme that I'm aware of, and holding it for a significant length of time, potentially. That means they just throw another transaction in. Miner, because you transaction, but directly paying it, so the bigger miners will be more profitable, right? And it doesn't matter, actually, whether you can to reduce them, and that if that drives centralization, so be it. You won't care, because your transaction will get in. You can take a whole pile of these transactions, stack them together, and add a... How would you do this? Well, I have one design, which you could certainly poke holes in. You would basically, at the end of your... You'd put something in somewhere. If we have 33-bit script pub keys, you get a few spare bits. You could chuck one in to say iteration, check sig, and introspection. They would all behave as if you were the only thing in the universe. If there's no end marker, that means your group, who you throw some sats at, throw them in your transaction, they just stack them all together and they attach a fee output. And anyone could do this. Yes, it is trusted, but it doesn't have to be a miner doing it. There is some reputation that would work in this case. And of course, if all else fails, you just do it yourself. Your stack of one idea, which competes with us, which I'm only valid if I immediately follow that for several hundred. Rather than stacking transactions, you would just turn them into this road train of transactions, and right at the end, you would have your sponsor that's paying for everything else. We went around way too long yesterday on this. It does end up costing you about 40 more weight per sub-transaction to do sponsorship. It's slightly more efficient to do stacking, but you could also argue it's more work to do stacking. So I'm leaving this one open. I just wanted to make sure everybody knew that we are going to have to do something along these lines so that we can handle the fee issue. Okay, there's a whole pile of bike sheds to paint and to-dos. I said the total stack limit, 520K, is obvious because it doesn't change anything. But I can't find anyone who knows. Does anyone know why the limit is currently 520 bytes per stack element? Right, yeah. Oh. Right. Okay. That's the best one. That's better than the 8-byte prefix on a 512-byte pile of poop. Okay, I'm going to go with that one. RSA, so Andrew Polstra suggested that there's a hypothesized reason that you can fit an RSA signature in there, which is true. And that in some pre-Bitcoin, they could have used RSA, and hence that. You can see the bones of that design carried through in the 520-byte limit. The truth is nobody truthfully knows why. Unleash that a bit. And we could say, well, a transaction can be up to 4 megabytes. You can have 4 megabytes on the stack. It means you can drop a whole transaction on the stack. 4 megabytes, not 4 million bytes, would be a reasonable stack limit. It does increase the runtime requirements of your Bitcoin node, but nobody cares. Like 4 megabytes is not going to cut the difference. Benchmarks, right? My laptop's not a canonical thing to use. We do need a broad range of benchmarks to establish relative costs across a whole heap of different machines. I've got to implement opdiv. We do need a full script for things so I could benchmark it. You actually need to write the code and do it properly. And then you're like, well, cider things properly because we can do it badly, so let's do it well. You know, but there's a whole question of like, while we're here, what else should we do? That is a whole thing that basically is the next 4 days of talks. What other things could we do? And I only have 45 minutes, so we're almost at the end. Summary. So when I suggested that I hated 64-bit arithmetic, well, that rather than 64-bit arithmetic, we should go for variable length arithmetic, Anthony Towns pointed out to me that actually this is a return to Bitcoin 0.3.0. I hadn't realized. I knew all the opcodes had been thrown away, but I didn't realize that originally we had variable length integers in Bitcoin. More broadly, the script system that we ended up with after the emergency response to the CVE, when everything was on fire, is like this strange, awkward thing, right? Not the programmable money that we all envisaged. But a full restoration of script does more than bring back something that we lost. It lets us evaluate ideas. Iteration, segmentation, these are ideas that came around because people wanted to make vaults, right? And new ideas are much more powerful and concrete and able to be assessed and evaluated when you can express them in script itself. And then if the new idea is useful and you can't do it in script, why can't script do it? Why don't we fix script? So, and finally, script, being its full self, lets us evaluate future optimizations, right? We can see how much it would improve based on real usage, right? And don't worry, there's still going to be plenty of things we can argue about. But if someone proposes a new opcode, even if you would never use it, you can see how much it would optimize on-chain usage that other people are doing and leave more room in blocks for stuff that you do want to do, right? And in the extreme case, we can even consider new key types. If there's some script that everyone's using, we can go, cool, let's just make that a new key type. And it expands internally to that script, right? In the next 4 days, you're going to hear some amazing ideas. And I've spent my entire 30-year programming career building tools for other developers to build things that I can hardly imagine. And sometimes they've been stupid, and sometimes they've even been evil, but the vast majority of them are brilliant and fantastic. And I can't consider that we would want to do anything short of giving them the best possible tools that we can build. Now, we need to put in the work, and it needs to be thoughtful, and it needs to be thorough, and it needs to be methodical. But nothing here is novel or even conceptually complex. It's just engineering. And we've done much harder things in Bitcoin already. Now, if my own children should take an interest in Bitcoin one day, I hope they get to control their own money. And I want doing that to be as natural and expressive as it can be. And if you feel the same way, I hope you'll continue this journey with me. Thank you.
Ladies and gents, thanks, Rusty. We're going to have a very short break. If you guys want to grab another cup of coffee, use the restroom, we'll have another talk on here in 5 minutes. And also, Ken's talk is going to be beginning in the Our next keynote speaker, researcher.
Okay. My name is Sergio. Introduction to BVMX, a CPU for Bitcoin without any change, without any soft fork or any hard fork. You can find me on Twitter, an SD Learner, and what I do is science research in Rostock Labs. Rostock Labs is the main contributor to the Rostock sidechain. And also I work for Fairgate Labs, which is a research pioneer in privacy-preserving technologies and especially in multi-party computation. So what's the motivation? Why we started looking into this new invention of BitVM? Well, we created in 2015 the Rostock sidechain, the first Rostock sidechain, which is the largest and longest run of the hash rate of the Bitcoin miners mining Rostock since 2018 when it was launched. It fully contributes to the security of the security budget of Bitcoin by providing transaction fees to Bitcoin miners. So this is really the evolution from a standard federated multisig into something that is much stronger in terms of security. We have signing keys that are tamper-proof, state-of-the-art technology in there, secure elements based, 5 out of 9 signature threshold. These HSS don't make them sign anything you want. They sign what. So this is great in terms of anyone can participate securing the spec. And you know, we could do better. We have been trying to do better since we launched. It was a huge event that in a blockchain, right? Maybe this is not necessary to go. You want to have DeFi embedded in the blockchain and not in a centralized channels. I know there are many Lightning developers here, and what you could do if you have a little more computation is just create for sidechains such as Rostock or rollups. You can verify the state transition of rollups in Bitcoin, which basically makes rollups really allowed to exit the funds at any time. And maybe you can have a new idea for a new L2 and verify that on Bitcoin sidechains. Why? Because Bitcoin itself, it's a store of value, and trying to make it more, responsive doesn't make sense at this point. Like, it's much better to work with a sidechain or a rollup where you can have a 5 seconds interaction with the blockchain, and you can have a more better user experience for the payment thing into a sidechain or a rollup. Then this would be great for Bitcoin. So I'm particularly interested in decentralized Bitcoin. How good is Bitcoin in terms of computing? I bring this slide. Do you know what is this? It was never actually built by him, but it was designed in the 80s, and it had 16 kilobytes of RAM, and it could do addition and subtraction in a single step, right? Quite a powerful machine. Play with the Atari 2600. I did when I was a kid. I played a combat game, and this machine had 120 bytes of RAM. But you could have with banking, you could have 64 kilobytes of ROM, but it could do addition, subtraction, division, multiplication, bitwise operation just in a single instruction. It was super powerful. But now we have Bitcoin. How good is Bitcoin compared to these machines? Well, in theory, we have this stack that has 0.5 megabyte of space. We have this tape, which would be the script part, very limited instruction, like we can add, subtract, and check a signature. But if we want to use Bitcoin, as is today, as a general purpose computer, 1,000 bytes, because you will finally be operating on bytes, and you only have 1,000 elements in the stack, so you're super restricted. And the tape, if you want to do multiplication and you have to implement that by hand, then the whole, let's say you want instructions. So you add this bitwise operation, but you end up having a curse. We have this problem of the opcodes that have been disabled by Satoshi, like most of the arithmetic, like a hash function in Bitcoin script. So you are very limited. So computation on the blockchain is expensive. Like executing 10,000 opcodes in the Atari 2600 would cost that amount of dollars in electricity, like less than a millisecond. And in Bitcoin script, the day I checked, it was more than $200. So there's a huge difference between computing on your personal computer and doing that on Bitcoin. Yet, we still want to compute some things, very small things, on Bitcoin. So it turns out that Bitcoin, thanks to ChatGPT for the image, it turns that Bitcoin is a kind of a calculator that only does addition and subtraction and has this fantastic button, I would call it play Tetris, where it does a lot of functionality, which is actually the check sig, but it's super restricted. Some people have tweaked check sig to do something else, like oracles and discrete log contracts, but essentially it's like very limited. So how can we compute on a blockchain and on Bitcoin in particular? Well, there are many models that have been pop up during the years. So we have the off-chain trusted computation model. This has been tried many times, like having oracles doing the computation and then voting on chain. Of course, we are not interested in this because this is not really decentralized. We can have Bitcoin script model where we have a non-Turing complete machine and it's bounded by the space of the program. So that's Bitcoin or Litecoin. Then we have the meta computation. This is what Rootstock and Ethereum do. Like you are allowed to create any kind of programs, Turing complete programs, but we are going to charge you for everything you do. We have this new, well, not so new idea of proof of computation integrity, where we don't actually run the whole thing, the whole program, but we just first create a proof that the program works, and then we just have to verify the proof. And that is the snarks, starks, and have been implemented successfully in Zk rollups. And then we have this final model, which is the disputable computation, sometimes called optimistic computation, that it was pioneered by TrueBit, and it was used also in rollups, and Robin brought this to Bitcoin with BVM0, the tap leaf circuits paper, and then he improved it with BVM1. Now he's working on BVM2, and we took that as a base foundations to build BVMX. So what is happening with all these different projects? Well, BVM0 is a kind of proof of concept, like a theoretical result. Nobody will ever write a snark verifier in logic gates because it takes terabytes of data and billions of gates. Then there is the BVM1 CPU. This was the previous projects of Robin, and it's now deprecated in favor of BVM2, which is under development now, so we don't have something to play with. And also there is no paper on this, but he's preparing one. And we decided to take the idea of the CPU, the general purpose computer, and create BVMX, which is basically a meta CPU because it allows you to create any kind of CPU. But we are, in the first project, we are focused on implementing a RISC-V processor. So to give you an idea of how it would be to do a dispute resolution in Bitcoin, probably most of you already know this, but for the new ones, we have two parties here. Patrick, which is the prover, he wants to prove that certain program given certain input verifies and accepts that input and can release the funds. And we have Valerie, which is just an observer that she follows the consensus rules. And so there is a verification program that is actually our script pub, and this is put on a standard output and is verified by the input given the input. So it's very simple. Then we have the snark idea that instead of doing the whole computation, we will just create the verification program will be just a function that verifies the snark. We will take the whole program and we will prove the program works with a small proof. And what we actually verify on chain is a small proof. And we think the first thought is, oh, maybe we can use that on Bitcoin. And this was what Gregory Maxwell thought in 2013. So he actually was one of the first to bring this idea into Bitcoin. He called it coin witness. And he said, okay, when these systems have evolved, we will be able to bring this into Bitcoin. that never happened, but maybe one day it happens. But the problem is that even if we could verify a snark in Bitcoin script today, it turns out that the verification program for Bitcoin script does not fit into these 400 kilobytes. Like the full computation, of course, it doesn't fit. The snark computation does not fit either. So we are stuck. So here's where the disputable paradigm comes. So the idea is now Patrick is the prover, but he's also a responder to certain challenges. And Valerie, instead of having a passive role, she will become a challenger. So Patrick will say, okay, I want to take the money from the UTXO, and Valerie will verify this locally, and if the computation is wrong, she will actually participate in a dispute resolution protocol. So what we have is a protocol that takes several transactions, and there are several script pubs, several programs run in each one of these transactions, and these transactions are pre-generated, like if it was a covenant, they are pre-generated by a certain committee. They throw away the key, so nobody can, generate another key for this committee, and then they can execute the protocol. In our particular case, we are now working in the two-party case, so we don't care much about this covenant thing, because the two-party will collaborate creating the transactions. So very simply, the protocol goes like this. There is Patrick. He says, I'm going to withdraw the Bitcoins. This is the program input that makes the program accept. Then Valerie will run this locally, and she say, okay, no, you're a cheater. She knows it because she ran and knows the result locally. Let's resolve this dispute on chain. So what Patrick will do in the BVM1 protocol, he will Merkleize all the steps of the program, and in each one of these steps, he will Merkleize all the RAM. So basically now they can do a binary search on this data structure and find the step that is wrong. So Valerie will say, okay, tell me the mid states, the hashes of all these particular intermediate steps. And Patrick will give her the mid states signed. And so Valerie finds the wrong step, and then she can go into the blockchain with the signed inputs and outputs that Patrick has signed and the step number, and just evaluate that on chain. Just simple step of the whole computation. And of course, it's billion times lower amount of computation. So in comparison, we can actually verify a RISC-V step with 1/4 of the size of a standard taproot script size, like 400 kilobytes. So this is feasible. So now, what's the novelty here? What have we been working on? So we've been working on a new implementation and a new design for this kind of CPUs, different from Robin's. And the aim of the whole project is not only to publish, but to create an implementation that is secure, extensible, open source, peer-reviewed, completely agnostic, that you can use for any kind of project, to do this on Bitcoin. And there is 2 organizations we have committed time and funds to make this happen. Of course, the project is open source and is open to the community to collaborate. We would be super happy if you want to code with us. Now I'm going to dig into the protocol, and I'm going to mention the building blocks. What are the things we need first to know to do the protocol? So one-time signatures. Because we cannot use ACDCA or Schnorr signatures because there is no check6 from stack, we must implement our own system for signatures. And this is something that has come up in many other, from other people, is using Lamport signatures. And these are one-time signatures. So it's basically as easy as a public key signature scheme. There is a key generation, sign-in algorithm, and a verification algorithm. The only restriction is that you don't sign 2 messages, different messages with the same public key, just one. That's the only restriction. And the size of the messages tend to be long. The size of the signatures tend to be long, and the public keys too. So how to use 1-bit Lamport signatures to do these one-time signatures? So essentially, the public key is 2 hashes, 2 hash digits. Let's call them Q0 and Q1. And the private key is the 2 pre-images of these 2 hashes. Let's call them P0, P1. So it's just very easy. If I want to sign bit 0, I just publish P0. and never publish P1. And if I want to sign 1, I just publish P1. And it's very easy to verify. I just hash and check if it matches Q0, Q1, or if it doesn't match anything, then it's not a valid signature. It turns out we can implement this in Bitcoin script. It takes a fair high amount of bytes, like 32 virtual bytes per bit, including the input, because the input is a hash, and then you have to test. So the signatures become a bit longer. But we can do better. And this is also an idea that several people had at the same time, is instead of using Lamport signatures, let's use Winternit signatures. And Winternit signatures, what they do is, instead of signing bit per bit, they pack many bits into a single digit, and then they sign the digit. So they build a hash chain, let's say with L steps, and to sign any one of these steps, it just gives the intermediate slot on this chain. Okay, so the last pre-image is, let's say, call it 0, and the last one is L, or the reverse, whatever, and then you basically can give away one of these intermediate hashes. Of course, you can forge signatures, and so there is a mechanism that is called the checksum to prevent an adversary from using the intermediate hashes. I call it the pulley, which is basically having a checksum that has the inverted sequence. So if you want to try to fork one, then you are forced to give the preimage that you don't have. Very easy, okay? And when you implement this in Bitcoin script, you can do 25 virtual bytes per bit. So that's much better. Still not perfect, but it's better. So now we have a mechanism to sign data in Bitcoin script. This allows us to create stateful protocols on Bitcoin script, provided that we already have this direct acyclic graph of pre-signed transactions that form the covenants, right? So if Alice signs a message X with her public key, Bob can use this X element signed at any later time. And we only need that the previous transaction in the script pub validates that this signature is valid by reusing the same public key. So Alice can create a message, and Bob can use it at a later time. So we have statefulness. But if Alice wants to use her own signatures, then there is a problem, because basically she can create forgeries of that signature. So every time Alice wants to use her own signatures, then we have to give Bob the possibility to challenge that and prove equivocation. Proving equivocation is very easy. Just present two values, x and x prime, with their corresponding signatures for x and for x prime, and then you can verify in Bitcoin script that these two messages are signed by the same public key, and you can punish Bob for this. Punish Alice for this. But it turns out that if you use this scheme, it makes the protocol design kind of complex, because you have to keep in mind that every time you use a value, you have to give the other party the opportunity to challenge. So what we decided, just to simplify the protocol, is do countersigning. So every time Alice signs a value x, then Bob comes and signs x again. So at that point, both of them can use the value x that is signed, and Alice will choose to use the x value that was signed by Bob, and Bob would choose to use the x value signed by Alice. So very easy. So now we have this building block. We can link messages and create a challenge response dialogue. So what Alice is going to do, she's going to sign a value x. Let's say that x is a step number she wants to query for more information, for a hash. And what Bob is signing is the concatenation of x plus the response. And the response will be a hash, probably, okay? So these two values get paired, and you can basically take these two values and put them back in a later stage of the protocol, and nobody can fork that. So now that we have the building blocks, I can tell you more about this BVMX meta CPU thing. So first, we can do whatever RISC architecture we want, like 8 bits to 64 bits. There is no limitation on that. We can do practically unlimited memory. Like it's bounded by, not really, because we only need a number of rounds which is in the logarithm of the amount of memory, so we are good. Any number of word size register in our CPU we can code because we are using memory mapped registers, so it's like memory. We obviously have a program counter, and each instruction can do any number of inputs outputs. So eventually you could also implement a CISC processor on top of this. But we are really interested in implementing a particular RISC-V 32-bit CPU. Why? Because it's super general purpose, and there's a lot of tool chains to use it. So RISC-V is license-free, royalty-free. It's a specification. It has 32 memory map registers, arithmetic operations. You have a memory operation, loads and stores, a 32-bit memory space. All access are aligned to memory, so that's good because it saves us to read one additional potential value from memory. So if you want to do unaligned access, you just do it in software. And well, instructions are also easy because they are 32 bits in length, so very, very simple to code. So now that we have the processor, we create a full trace. So when we execute locally the code, what we produce is this, what we call the full trace, where we write for every single step of the computation these values. For the inputs, we write 3 values. 2 reads, one would be a register and one would be a memory access, if the instruction requires both, and a read of the program counter. And for each one of these reads, we record the address that was read, the value, and this is the difference between other models. We record the last step where this address was written, okay? And from the output, we record the address and the value that is written and the program counter. And there is a smaller amount of information that we call the trace or the write trace, which it's only the step number and the writes. We don't care about the reads. That's another interesting thing. So now that we have these traces, we can build a hash chain, not a Merkle tree, but a hash chain where each hash, we start from a fixed random value like 0, and at each step of computation, we hash the previous step, hash digest, and the trace, only the outputs of the instruction processing, and we build this for the whole computation. So this is very fast. Like, you can do millions of hashes per second. So what is interesting is that you can, for each challenge, you can just run your computation over and over. You don't need to store this information because you can just grab the information you need. Or you can put some checkpoints in certain places so that you can do faster in the future. But essentially, it needs no memory, only to store temporarily the last steps that each memory cell was used, right? And so there is a verifier decision tree where he chooses what to challenge, and instead of going through the theoretical thing, we'll go into a particular example to show how easy it is. So as I mentioned, at first we have a binary search where the verifier asks for a specific trace step hash of specific steps, and the operator responds with those step hashes. So this is simple. So let's take an example. Let's think that we have only 16 steps of computation. We know that step 0 is correct, so the step hash of step 0 is correct because this is the initial step. And we know that step 16 is incorrect because, if not, we won't be challenging. So we challenge because the last step is incorrect. And so we will ask, obviously, for a midpoint, let's say step 8, and then the operator will tell us the step hash. And in this example, step 8 is correct. So we move to a midpoint between step 8 and step 16. We have step 12, and then we move on this binary search. And finally, we have 2 steps, in this case, step 11 and step 12, where we have some kind of malfunction, right? Something is wrong about step 12. So 2 things can be wrong about the step. Either the write operations in the hash chains are incorrect, like the operator is cheating about what is the result of executing this instruction, so the outputs are wrong, or it could be the case that the outputs are right, but basically the the operator is lying about how the hash function operates, okay? So what we ask to the operator in this case is a new challenge where we ask the full trace of that instruction. We only had the hash, now we want the full trace of that operation. So the operator will bring all the read values, each one with this last step that was where this memory address was last written, everything. And now it's very easy to find out where the error is. So if the error is in the program counter, it's very easy to challenge because you have the previous step, which is correct, which writes the program counter. So you only have to show, the previous program counter and new program counter, and if they are not equal, then the program counter is wrong. If the writes are correct, then we can challenge the hash function. So that's very easy. We only need to code SHA-2056 in Bitcoin script. We have already done so. Martin here has made an implementation that is below the threshold of standard transaction, and we can even split that in chunks with mid-states. We can make it for very low amount of Bitcoin script, so we can challenge the hash function. But the worst case would be, that the writes are incorrect because of the reads. Like, the operator is telling us that he has read from memory, but he's lying about the address or the value or the last step. Something is wrong. So the easy thing is, what if the last step is correct, the value is incorrect, and so, but the step 5, here the last step that the operator tells us is step 5, but this step 5, he shows us the step hash, and the step hash is correct, but it doesn't matches the value written with the value read on step 12. Well, this is the easy case. We just challenge that. I mean, we have a good hash here and a bad hash here. One is writing a value, the other is not reading the correct value. Easy, very easy. Well, what happens if the last step value is incorrect? Maybe the prover tells us the last use of that memory was in step 3, but we know from our local execution that it was used in step 5, and a different value was written. So this is the interesting thing. We know that step 5 is incorrect because we have run this locally. And we know that step 11 is correct. So now we are in a scenario which is the opposite that we have at the beginning. At the beginning we had a starting step that was correct and an ending step that is incorrect. And now we have the opposite, a step that is incorrect that ends with one that is correct. And this should immediately raise an alarm. I mean, it's very easy to prove that there is no hash chain possible that can convert a bad step into a new step, into a good step. I mean, we had to break the second pre-image of this hash chain. So, and we can do even better. Like, we already have some challenges previous to step 11 that tell us good steps. So we run a new binary search only between those two steps, the incorrect step and the correct step, until we find a magical recovery of the computation, right? A place where there is an incorrect step followed by a correct step. And now it's very easy. We just challenge the hash function. Like, it's impossible to come up with a different write to registers or memory that can turn a bad step hash, in this case step hash number 6, into a good step hash, which is step hash number 7. So basically, we've solved all the problems of memory access, memory writes, execution. Oh, I didn't mention, but if the writes are incorrect and the reads are correct, we just challenge the step of execution. That's also very easy. Just one step of processing, and we can show that this instruction does not create the right outputs. So we've covered all the cases. There are some other cases related to how to access the program input and how to access the program ROM, where the program is stored. That's on the paper. You can read about that. But this is the good stuff is this. We can improve it by doing, instead of doing a binary search, which was something that Robin did in BVM1, we can do an NRE search. So instead of the prover giving just one middle hash or just one hash, he can give several hashes equally separated in the space, and then we can make a trade-off between the round complexity and the cost, the transaction cost. So it's tunable. We can find a sweet spot where we feel that we can spend that amount of money and do not delay the protocol much. And we can do even better. Instead of transmitting the full step, we can just transmit the small prefix of each one of the selections in the space. Tomorrow at 10 o'clock, Ramon and Javi will be giving a workshop where they will code this and show us how to do this binary search in Bitcoin script. So you will be able to play with this with their help. So how is BVMX compared with BitVM in a particular stance where we want to verify a snark, which is generally the most common case? So if we take the gate-based BitVM0 protocol, and this is just a theoretical comparison, it's not very important in practice, it's much better. Like, it would take weeks of preprocessing and terabytes of storage. But if we compare with BitVM1, we can do it with a lot less preprocessing, basically almost no preprocessing, and just with much less memory. And with a little less on-chain cost. Like, we estimate this because BitVM1 was never built, these are only estimations, right? But we estimate that it would cost like 300 kilobytes in BitVM1, and we think we can do with 200 kilobytes. And another interesting comparison is against BitVM2, which also not finished, but is super promising. And it can solve the dispute in just one round, but you need to post a huge amount of information in the blockchain, like more than 4 megabytes of data. So this may cost you 100K maybe in transaction fees. It may be very good for maybe for multi-party, but yeah, it depends on the use case. But generally, it would cost a lot, and you would only use that for very high amounts of money. And of course, we have a Bitcoin opcode wish list. Like how this could be improved if we have more Bitcoin opcodes. Well, basically, I'm not going to the detail, but basically, this would take, if we had all these opcodes implemented, like it would take like 20 kilobytes to solve any dispute, from 300 kilobytes to just 20 kilobytes on chain. So it will very cheaply. At today's cost, it can be like from 3K US dollars to yeah, a couple of $20 or maybe. So we have a roadmap with the resources and the people we are working on this to finish this in 1 year. We've published the BitVMX paper. It's ready for you to download now in the BitVMX website. Please take a look and send us your comments, your new ideas. Please come and contribute to the Telegram channel. The next paper that we are already working on is about extending the two-party protocol to n-party protocol. And there is a lot of open questions and very interesting challenges and how to do that very efficiently, minimizing the security bonds. And then we will do a release of this code, and releases we will try to do on a periodic basis, right? But we plan to do a full release of the n-party protocol, and finally a last release with some optimizations by the end of the year. This is a, I mean, maybe you want to attend. This is a Bitcoin Rootstock meetup that is happening today. And if you want to learn more about Rootstock sidechain, please come to this meetup. I'll be there to answer more questions about BitVMX. Several people from the BVMX team that are collaborators are here, and they will be there too. So we can have a great chat about BVMX here. Yeah, that's all. Hope you visit our site and come to our Telegram channel. Send us your comments or proposals, or if you want to code, we will welcome your contributions. And I don't know if there's time for Q&A or we are done. Okay, 2 questions, if there are any. Yeah. Well, the closest you can have without interactivity, which means, yeah. Yeah. Yeah, I mean, if we have covenants, and then if we have like multiplication, then I think the best approach would be just to do it in a single script, like split in parts, like BVM2 idea, and then you would be able to do it in one round. But I mean, Rootstock, from our perspective, we cannot wait until that happens. Like, we've waited so long for forward at full speed, because there is a lot of users and active users in Rootstock that they want a more decentralized reach. Okay? One more question. John?
Clarifying question about the comparison chart. You noted that BVMX puts 200 kilobytes on chain.
Yeah.
Is that over the entire string of challenge and response transactions, or is that per?
Yeah, it's about 300, and it's the whole protocol. So it's a very short amount of data. And you can do some trade-offs between data and round complexity, right? By doing these NRE searches. These are estimations. We haven't coded, but in paper, these are the amounts. Okay, thank you very much. And to
I look like Britney Spears. Oh, that's on. I guess we're going. All right. Amazing people. And then there's me. Yeah, I got it. They asked me 2 days ago to do this panel. Lisa called me up. She said, "Do you want to do a panel on covenants?" And I said, "What are covenants?" So, I can't really move this, can I? Can we move this? Let's get rid of that. Let's show everyone's face. I go by Junseth. Many of you know me. Most of you don't. Some of you are my friends. Most of you aren't. But today, we're just going to talk a little bit about covenants. So we're going to structure this panel. It's real simple. I want people who are watching at home, and anyone in here who, there's probably actually not anyone in here who's in this position, but people here anywhere that have discussion about the differences between all of the proposals. I'm going to have them talk about the advantages, disadvantages, and then in the back we have a little pool. I'm going to bring it up here at the end, and Reindel and Rusty are going to wrestle in the mud with their shirts off. So I think we'll just start at the beginning. When I started this, I really didn't know much about covenants. I've said this for a while, many years. Many of you are still like that. I am not as much like that as I was. So when Lisa asked me to do a panel on covenants, I had to go watch a lot of Andrew Polstra videos and a bunch of other people talking about them online, and learn as much as I could about them to do this panel and talk to you guys as if I had any competency whatsoever. So here we are, and I'm excited to do this. So let's talk a little bit about like what covenants are. Let's do like 3 or 4 minutes on that, and then we'll move on to the rest. All right?
Sure.
Great. Reindel, you go.
Yeah, so in Bitcoin script, we normally have a way to encumber coins on a set of conditions or predicates that apply to the inputs of a transaction. So you can say, you're allowed to spend these coins if you can produce a signature or or how they're spent into the future. And having some conditions about the future spending of a UTXO is what covenants are. And then all the rest of the discussion is what's the right shape.
Covenants can be even more general than that. The most common thing we are talking about in Bitcoin right now is those future output restriction covenants, but you can envision other kinds of covenants too. This is just the current conversation is focused on those. But actually the CCV covenants can also be input-facing and apply additional, more output forward-looking covenants.
And I'm realizing as a moderator, I've shirked my responsibility. Let's introduce everyone first. All right, I'll let you guys introduce yourselves. So let's start here with Brandon.
I'm Brandon Black. I work at Swan. I also go by Reardon Code on the Hellbird site, the ex-Hellbird site. I've been working on Bitcoin self-custody full-time for about 6 years now. So the reason I'm here talking about this is better self-custody options.
Yeah, I go by Reindahl on Twitter. I'm the CTO at Taproot Wizards. We're known mostly for making illustrated children's books and occasionally non-standard transactions.
I'm Johan Halseth. I do open source Bitcoin development at NIDIG, and I'm currently researching and developing use cases using covenants, and my preferred one is the check contract verify.
There's a fan.
Yeah, it's a good one.
Hi. I'm Rusty Russell. I'm a lightning person. What am I doing here? Lisa was running this conference, and I said, "Oh, cool, I'll talk about it." She said, "It's about." I'm just going to here to listen, really. They didn't even give me a mic.
That's true. So there's a.
Well, it's a multi-party mic, and you have to control who's allowed to use it.
So based on the explanation, I mean, so covenants basically are the thing that allows us to program, let's say like when you put Bitcoin into a wallet, that money is sitting there, and you can program things like, I think the vault is probably the most specific example. You can say this money can only be spent if it goes to this address first. Is that the?
Yeah.
So that's one way that you can script it. So covenants allow you to do this kind of behavior with Bitcoin.
It all, as they said, it allows you to kind of like restrict where future spend of the coins, what restrictions there are, and there also an extension to that situations.
Cool.
Yeah. So yeah, the term covenants, because it's the output restriction thing, and it's not really just covenants, blah, blah, blah.
Yeah.
We think about it at a script level as introspection. You can add very, very limited today in script, and if you open that up, you can do all these cool things. So covenants are kind of a side effect of the mechanism, which is introspection.
Yeah, I mean, maybe just to like poke on that a little bit more. If you haven't spent a lot of time with Bitcoin script or trying to implementing things in Bitcoin script, you might intuitively assume that you can do things like inspect the value of an output, or inspect the destination of an output, or know what the sequence number was for one of your inputs. And you don't actually get access to that kind of state in script. And so
you almost get the ability, and if you add a couple of things and squint sideways, you can. There's a good talk coming up about this.
Yeah, that's right. In like an hour.
So we've talked a little bit about this too. So can we do a little bit about the history of covenants? Where do they come from? Like, where do they start? Where do this goes back to Satoshi, right?
I mean, covenants are a legal thing. Oh, sorry. So covenants are a legal thing, where when you sell something, you.
I guess I mean scripting in Bitcoin, like covenants in Bitcoin,
right?
Like opcat.
You said go back.
Yeah.
All the way back.
You place the restriction as you can buy this, but you can only sell it to whatever, or things like that. They're often used for evil legal purposes, but they can also be used for this.
Yeah.
Yeah.
And
for vaults.
for vaults, they needed covenants.
They needed covenants so that you could do this inspection thing, and then it kind of took off from there. So that's kind of the history, and then we get into the whole how should we do it. And they're like that, I guess, is why we have a
And that's where Polstra gets into it,
back
is the how.
Back when Bitcoin was first designed, Satoshi had like a number of things that would have allowed you to do these scripts in Bitcoin, correct?
That I'm not sure it was deliberate. It's just, there was a programming language, right? And it turns out you could do an awful lot. A general, and one of them was we would have had the ability to do.
Well, I think we can say that Satoshi didn't add introspection. But
not
he
explicitly,
had, not explicitly, but it had cat, and
with cat
you can do it.
Could you do it
in
without
certain
Schnorr?
ways. You could do it with ECDSA as well, but
it's
it's
a
very
lot cleaner with
complex.
Schnorr, but you can technically do it with ECDSA.
Okay.
Yeah.
Okay.
But I don't think
One of the proposals on the table currently for covenants. What are the others? Like I know, Brandon, for example, you're into a different one.
Yeah, so I really just picked up what Jeremy Rubin had been working on with Verify or CTV, and the observation about CTV is that it's with checksig from stack and internal key to make what I call L-enhance, and I consider that the kind of minimum useful set of let's get covenants into Bitcoin. That's kind of what the debate is. What is the minimum useful set of getting covenants into Bitcoin to make good news?
Yeah, that's right. I mean, you can do it with Opcat. You can do it's amazing. Like, I'm really impressed, and I'm looking forward to your talk.
Yeah, it should be fun.
But yeah, it's also a little bit of a
situation where you can do everything, but it's not optimal for any of those things.
So Randall, you're the most controversial person on this panel. You're
I don't know about
bit
that.
of a shitcoiner.
I don't know about that.
I think a lot of the OpCat discussion in current days has been tied in with and the is sort of the oldest of these protocols.
Yeah, we want to bring it back.
And
there's a song
I heard.
Yeah.
And let's talk a little bit about that. Just tell us
song.
about OpCat.
Yeah, I mean, so OpCat was Satoshi wrote it. OpCat, we want to bring you back. So it's just concatenation, but there's a trick that Andrew Polstra figured out in, I want to say 2021. Wrote a really great blog post called Cat and Schnorr Tricks. I'm going to be giving a talk about it later today. Signature on the stack, just using cat and SHA-256, and then you do check sig with it. And if that check sig is valid, then it means that the message that you put into the Schnorr signature is valid over the transaction. And that lets you get different components of the transaction. These coins can only be spent to this destination. You bake that destination into your script, and then you pass in all the other components, signature, and want to have be fixed, and which ones you want to be variable. So you get, whatever. A big cat transaction is like 3.
OpCat's by a lot is that it's ugly, it's big.
Yeah.
It's not space
Yeah, I mean,
constraining.
it's to do something like OpCat is that it's so generic that we can let people go and build whatever they want, and then we can look at what people are actually doing with it, and if we see that really well, and we optimize this use case and claim back some chain space. So I think that that's the reason to do CAT is that it's used to build lots of stuff, including things that we haven't thought about before. And if we see that there's economic demand for specific shape,
No.
No.
Russ?
CCV.
Just CTV.
CCV. Check contract verify. Yeah, so check contract verify. As part of the Merklei's All the Things framework. And with that, we are also using to CAT, we have this CCV opcode. And the thing I like about it, you specify an input or an output, and then you check the root hash of the tap tree, and you can check what's the tweaked with some data. And you can do that on the inputs and outputs, and within an input, then you can do some computation on that state, and then you can commit to I'm going to talk about in my talk later, very complex computation into very simple operations in Bitcoin script. People are always afraid of modifying the script engine in Bitcoin, but what it's doing, that's one of the reasons.
ZK verifier op.
And it turns out with the building block, you can actually do that.
The thing worth pointing out here, I think, is that do everything that CCV can do, but it's ugly. Because if you do just cat, you're going to have.
No, we weren't. But that's it.
Yeah.
You're going to be very rich. You care about scripting. You care about scripting and the way you think about this problem in general.
This was so we had a bit of a angle that they come from, but it's the nuance. But there was no one. So I don't think I have a unique perspective. I don't think so. I think old, but thank you. But you will do the best thing you can, and sometimes it'll fuck up, and it'll be terrible, and blah blah. Most useful to the most number of people. That what do I think is genuinely the best? So maybe we need to. That is consistent with or is it just straightforward engineering?
This is how I buy a person in getting through the bit process. Is there a world where all
you can't try to? I mean, no. There are enough people in the world who will come at it from a political angle. What's politically possible? What's palatable? That is the best thing, and it will win. But there will be a shit fight. So that's why we didn't implement it that way. And now you've got we're still using 32-byte pub keys or whatever.
I think there's great engineering, and then it could be done anything to the Bitcoin protocol. Yeah. I think that's.
You have to get users to run the software. You can implement anything. You'll have to have a reason to do that. And I think most users of Bitcoin are going to want that they want to do with their money. And I think a little bit tools that are close at hand, and then how do we use those to want to be able to do with programmable money, and then work backwards from there. Changes that I just don't think that the network is.
Sounds like I looked at this.
Me last night. I did some.
As a generality,
unique. A conversation about SIG hash flags usage on the network that's using SIG hash single anyone can pay. And that's
Rusty, how do you know that there's no unforeseen consequences of like expanding scripting with OpCat? Well, okay, so other than the cool stuff, I just mean like maybe Bitcoin breaking type problems or something like that. How do we
blow the network up, right? We do make sure that it's straightforward. But so okay, this is an important principle.
Capper wizards?
Yeah, I know that thought experiment that I really should trace back. And this that single block, and we just die. It's a risk. People doing dumb shit with more money than you is a problem, right? But it's not a problem we can solve. Money, and if you have a solution, that's awesome. But I don't.
Well, I mean, or another example is the class for a really long time where you can only spend your coins to somebody who has a social credit policy server. There's actually a product on the market that does exactly this for registered assets. It's called AMP.
Blockstream. What's interesting actually there is that you don't want that. Like if you're evil government and you're trying to control it, you don't want
covenants.
You make the conditions, right? So you really want a signature server, right? And you can do that trivially.
Yeah, and I think relatedly, with everything in engineering, there's also the risk of unforeseen consequences of doing nothing, because folks can self-custody Bitcoin right now. Like the Lightning paper originally said we would need 130. I'm not going to make 130 megabyte blocks. That's a bad engineering solution.
Yeah, that's fair.
It enables some Lightning stuff that the other
thing. But one of the things it can't do is Lightning symmetry or L2 channels, as they're previously called. And I think that's a pretty valuable use case. A cat, as magical as we all used to think it was.
I'd pick a vault over LN symmetry any day of the week.
No, I wouldn't. You see,
no.
Absolutely, because
actually, I don't want to.
Well,
sure.
I assumed that we would get LN symmetry, and it cleans up a whole heap of stuff in the protocol.
And what is LN symmetry? What's the
LN symmetry? Money, and I have to react to that. It's really interesting because the you screw up, I take all the money doesn't work with three people. Like you've got this toxic state, right? Previously,
symmetry,
like
same
you
state
had
on both sides.
Yeah, it's symmetry, hence the symmetry argument. But yeah, currently today, stay on the chain, you lose all your money potentially, right? Because they can use the penalty mechanism, right? It's almost too much, right? Whereas if all I can do is fix it up, they can get annoyed at you, and maybe there is some penalty have today.
The Deus et Machina of Lightning. We take it. What's that?
Because it's a protocol that has documentation that I can show. Yep. Here's an implementation of dates. There's a lot of other stuff you can do once you have this symmetric channel construct.
And symmetric channel constructs are the symmetric channel construct you're describing is something that only L-enhance at least is.
One of the maybe confusing things here as well is like most of these covenant proposals, like TXHash, you can do surprising stuff.
I was getting coffee this morning.
Enable sort of the same
kind of the same stuff.
Yeah. So I think the discussion is a lot able to do this thing very efficiently and compactly, or should we need to do this emulation to proposals?
Is it worth talking?
Oh, it's rough.
I'm not going to say, cool. Well, once we've got a really clean cat, so it gives us, covenants. So let's just round it out. Cat and then verify. So I don't know. We can have that debate, right?
Yeah.
But script without having to jump through hoops, and I think that's for it. We should maybe just write the cleanest thing we can and figure out what that is. Now, there is on this is, he tried to create this absolutely minimal sliver. It's very hard to do a tiny thing that doesn't open this door.
With the Bitcoin script, it's gonna get
better rather than trying to do this little nitpicky, like how small can I make it to avoid all these things? No, just do something good.
Yeah, do something good. But also, I think what's interesting has come out is that actually one of these is attractive, surely. For different people, it's different things, right? That's right. It's like, there's a new one every week. And so I am sure that...
What are the downsides?
Be painted. With this much code, it used to already be so small that it's this multi-number script restoration. There's a variable ops budget so that we don't blow up somebody's Raspberry Pi. Go do them.
Yeah, I think a lot of people talk about this, what's the risk is huge.
Yeah.
Huge.
Yeah.
But also, one's going to build something really bad for users using this. Okay, they could build that really bad thing. If we give them an option to get the same functionality in a good way that doesn't have these negative consequences, they're much more likely to build the good thing.
Yeah.
That it opens, hey, I see you building a dumb thing. So, restoration, we can start to undo that problem, so we can reduce risks.
Entering into the open market possibly gives you
things that are harmful to trees. You just throw them out, new token protocols, being anyone can spend output for some Rune, token with 0 consensus changes to Bitcoin.
Yeah.
It's bad. That's really the thing.
If anybody wants a hackathon project to completely destroy my...
It's hard to do self-custody.
Rusty, something you mentioned is that over the past couple of years, we've learned that we actually do want covenants. Why did it take so long to realize that?
So why wanted covenants?
People are slow.
On-chain fees were low.
Yeah,
Usage.
Yeah, actually, that's fair. Fees were low. Dude, don't worry, that's tomorrow's problem, right? And suddenly tomorrow's problem is today's problem. I think there's some of that. Ideas take a while to percolate sometimes, right? Particularly, I've noticed that bad news tends to get attenuated really fast in the Bitcoin ecosystem. Bullshit that sounds positive, wow, that spreads. But it does take a while for rising fees is going to be a problem for self-custody. That message is in the white paper. Not quite, but it's trivial to extrapolate. Everyone knew this, but suddenly people are aware of it. And yeah, I think it just takes time for these messages to get out, and people go, "Wow, we need an answer."
And I think actually Taproot made a huge difference in how people are thinking about covenants, because earlier, if you had complex covenant schemes with recovery paths and everything, it turns out, the scripts are huge,
script,
right?
yeah.
And then we got this Taproot update that makes it possible to split the scripts and make it smaller and hide them and do all kind of nice things from that perspective. And it turns out, okay, if I had a covenant in here as one of the paths, then I could do these amazing things. So I think Taproot helped just progress the discussion and get people thinking about covenants again.
And also just the engineering aspect of here we are in 2024, we're really just starting to see concrete usage of Taproot. So in a sense, Lightning itself is a covenant. And so now we have Taproot channels in Lightning where the force close paths are hidden in the tap tree, as John was just saying. And so that's now a thing, and that makes more apparent how we can benefit from covenants because the engineering has been done. So as Rusty said, there's work we have to do, and engineering has to keep moving forward.
Real quick, so in the last year, I've noticed that there seems to be a lot more businesses being built in Bitcoin that are using the scripting in Bitcoin. Maybe I just have been oblivious to it, but is that true? Are there more businesses now that are starting to utilize the Bitcoin scripting than there was before, and why? Why is it happening now as opposed to previous?
That's a really good question. I don't know.
Miniscript is part of it?
Yeah, Miniscript, we've got better tooling, but what came first, chicken or egg? People wanted to do things in script, so we got better tooling so people can do more things in script. I think it just takes a while.
And I think also Taproot makes it actually cheap to add more scripts.
Yeah.
To an output. Yeah. Earlier it's I can add some complicated script here, but it will be expensive, so nobody will use it, so let's just not do it. But
so
now we can actually...
Taproot gave us Miniscript and Taproot Wizards.
Well, Miniscript existed before. There is now Tap Miniscript.
And now there's a lot more businesses using script on Bitcoin.
Yeah, that's true, though. There are a lot of businesses. To me, that was a really sort of interesting observation the last couple of years. I've just seen more and more businesses that really do rely on the scripting in Bitcoin, whereas before I felt like people were using Bitcoin as money or as something very simple. But it's interesting to see sort of the complexity of businesses come up while scripting is being used more often.
Which also answers the previous question of why covenants now? And the answer is that people are actually starting to use script a lot more now, and now they're banging their head against these arbitrary limitations that were replaced. So I think that it also feeds into the why covenants now.
So Shinobi, is it you?
I just wanted to ask Rindell why he
Oh my God.
Rindell, Shinobi wants to know why you hate Bitcoin.
I don't. That's why I spend so much time making so many Bitcoin transactions. Because I love it.
He does make a lot of Bitcoin transactions.
Do you think Bitcoin could evolve towards an app with covenants from the beginning?
So the question is, do you think that Bitcoin could have developed to where it is now if we had covenants at the beginning, at the outset?
Because we did have covenants at the beginning, so the answer has to be yes. Yeah, but no, I think we're always going to go through the stage where most people were just sending money and happy with signatures.
Yeah.
Before it got to the point where people had to really, there'd always be some, people would have played perhaps a bit more than they did, although people did some weird shit.
We talked about it earlier, I think if you remember, Mike Hearn's Lighthouse was I don't know how many covenants it would, you could say it used, but it was an early sort of scripting product, and there were other stuff that people had tried back then.
It is interesting to think if we had the ability to do some kind of velocity control. I don't want to say vaults because that's too specific, but some kind of velocity control for funds. I bet the wallet ecosystem would look radically different than it does today.
Oh, see, I don't think it would.
You don't think so?
I
What
think.
in signatures?
Well, Bitcoin hasn't been worth anything until now. Like,
Well, that's almost true, right?
Yeah, it's
true.
Yeah, I don't know that people would have cared until now.
I remember sending a friend 7 Bitcoins because he bought me a sandwich, you know, and I don't remember what the fee was back. That was probably half a Bitcoin. It was just like, you know, Bitcoin.
Probably 0, actually.
It could have been 0
Well,
too.
I mean, like the
Bitcoin is
whole
worth,
like wallet ecosystem is really around proactive security, and like you have to make sure that nobody gets to your keys ever or money gone, right? And if we had some ability to do like flow control, or if you have a vault system where you can like claw your money back, then you don't have to be quite as precious with like that one set of keys.
So Green Wallet, it kind of is this, right?
Sure.
We do that. And demand is not as great as you'd think. You'd hope that it's climbing in the future, but
Yeah.
for now, people are like, I still have all my Bitcoins on my phone. And I just, I upload it to Google Drive. What's the problem?
Do you have all your Bitcoins on your phone, Leslie? And are carrying it with you now?
They're all in Google Drive.
That's right. No, all mine are in Mt. Gox.
No gox.
Whoever. I was going to call over here, but I guess I'm not seeing her. Let's go over here first. Vic. Okay.
Have any of you thought of half aggregation or the interactive full aggregation in conjunction with your proposals?
So have any of you thought of half aggregation or full aggregation in conjunction with your proposals? I don't know what that means. So can you explain what it means first, and then
I'll
answer
explain,
the
and then I'll
question?
take an answer if we thought about it. So half aggregation would be, you have your signatures, they're normally 64 bytes long in Schnorr. You can combine the nonces and keep the S parts separate, I think. No, you have to combine the other one. Hey, whatever. You combine half of it, so each signature takes 32 bytes instead of 64. And that makes your transaction smaller. And then full aggregation interactively is essentially similar to Music 2, if you've heard of that, which you can use for plain key aggregation, except that it would be across the different messages that different people have signed in the transaction and do it interactively. So you save the full signature. You basically have a transaction that has no signature cost to it, except for one for the whole transaction. And these are great because they would encourage things like coin joins, because the more inputs you have now, the cheaper your transaction gets. So we thought about it?
Has anyone thought about it? Yes, obviously, yes. So half aggregation is relatively easy because it's non-interactive and you can just set things up and you can go. There's some really rough code that I've seen to do it. And you can do that for you can do that in proposals where you end up with a so multi-party computation. You end up with a transaction holding their signature that could possibly be half aggregated. Maybe I haven't. Perhaps. It definitely cannot be fully aggregated because that requires interaction, and they've gone away. That's why you're trying to spend this. So it won't be used for all, it won't be used for all Bitcoin transactions. It simply can't. But for the normal, I just want to send some Bitcoin case, you could totally go full signature aggregation. But that said, we're still waiting on a lot of engineering, and I think there's theoretical work to make sure that it's actually sound.
Yes, and the thing with half aggregation is that while you can do it, you're only saving 32 witness bytes per signature. And in terms of percentages, your transaction weight isn't really reduced in a high percentage. So it is a worthwhile thing to consider down the road, but when we're looking at more trying to amortize the on-chain transactions, make them less frequent, using things like multi-party lightning or CatVM or BitVM or whatever, all of these things are let's make fewer Bitcoin transactions. And if we're talking about saving with half aggregation 4-ish% of our transaction weight, do we care? Is that the highest priority relative to enabling the reducing of transactions in the first place?
There's definitely lower hanging fruit.
Yeah. And for space savings, you can say that some of these introspection proposals actually gives you the possibility to do this because you can share signatures across inputs, right? So you can have a script that just like fetches the signature from some.
Or there might be applications where you just don't need a signature, or you need fewer signatures or something.
Yeah. So you don't have to like duplicate the data on all the inputs.
So I guess the answer is yes, but we're thinking about it, and it's probably less beneficial than some of the other things we can work on first, even though it's so interesting to think about.
So go to the beautiful mustachioed lady over here.
You're not Shinobi. You're not Shinobi.
No.
Can you actually speak on like why fear around MVP might stem from confusion over the approach to building of applications on Bitcoin versus other chain where all of the computation happens, on chain on other chain, and then we're trying to
So basically, you're saying we've avoided the MEV conversation so far. Can we have it?
Yeah.
Sure.
MEV is a lie.
Well, I think what we mentioned earlier, like whatever improvement you do to Bitcoin script, you're gonna get some sort of covenant or maybe MEV from it. So I don't
we
think
have this issue already today? Like, you could, you
You
create
definitely
some
have-
protocol that builds on Bitcoin that MEVs it. Like,
You definitely have MEV. I mean, like, I think Counterparty is probably the oldest example of MEV on Bitcoin, where people are paying to get these little tokens that aren't Bitcoin moved around Bitcoin, right? And they're paying little minor fees to do that.
and I guess ordinals as well. There's an MEV.
Bitcoin invented MEV in some ways,
Yeah.
right? Which is kind of an embarrassing thing given how we've critiqued it on Ethereum. But yeah, we've done it for a long time.
but I think in a lot of cases you can build protocols just smarter. Like, don't do that. If you care, don't do it.
Yeah, I mean, something that's interesting is like usually MEV, highly exploitable MEV that's really exploitable by a miner or a validator is usually the sign of a poorly designed protocol, and the users of your protocol are losing value to the miner or whoever the MEV extractor is. So if there's two protocols in the market and one of them exposes their users to having value siphoned off by whoever the sequencer is or the block producer or whatever, and another one doesn't, then that other one should, in a reasonably fair market, outcompete the one that exposes its users to MEV. So I kind of see a lot of the classic MEV scenarios as just being symptoms of badly designed protocols that just need to die or be outcompeted. And I also think it's worthwhile to remember that we have like 10-minute blocks, and that there's different games that people are going to play on Bitcoin than they play on other networks, and we shouldn't let a abstract specter of MEV stop us from building the things that people need to do on Bitcoin.
Yeah, I agree with you. I think it is a subset of the stupid people with too much money problem.
So as the moderator, we have time for one more question. So who's going to pay the most to be in this next block?
And he does take out of band payments.
So I'll let roast beef will have a good question, but roast beef, can we have someone translate?
Yep.
I got 13% of that. So someone.
The question is best extension mechanisms for adding things to Bitcoin script. Is op success the new thing added in TapScript, or is it the op nops? By using op nops, you get the access to bare script as well as TapScripts and also to SegWit v0. So what's the best way to extend script going forward?
Yeah, it's case by case. I mean, my general thing is, for God's sake, put it in TapScript. But also, we need to remove the internal key penalty for TapScript. That kind of goes without saying. Once you've done that, they're kind of basically on parity, right? Taproot at the moment, you basically need to put a dummy key in, even if you don't want it. It's 33 bytes, right? So if you get rid of that, solve that somehow, then they're kind of on parity. But then, yes, there are special cases where...
Yeah, opcat you can't op.
Yeah, well, some things you can't, or
And
cat
some
verify,
things-
I don't know.
Yeah, cat verify. Yeah.
Oh God, too many bytes.
Imagine all the bytes.
Yeah.
Yeah, I don't think so. I think unless there's a compelling reason, you abandon old script as like that's in stone and move forward.
And to give an example of a compelling reason, so CTV itself makes sense to do as a verify because you can make a bare CTV that is now literally the most efficient way to constrain future outputs because it fits into a 33-byte bare script the same way that you used to be able to do like a bare pay-to-pub key. And that's an extremely efficient way to constrain that with no witness needed to spend it at all. Other things don't make nearly as much sense. There's a conversation about roast beef right now about whether checksync from stack verify makes sense as an op or not.
I think we're done. Do we have time for one more?
JB55.
I'm being cut off.
Yeah.
I'm just curious if you guys thought of any type of data that you can introspect that would cause problems down the line if you use a certain type of data when you're introspecting.
If you were to do global introspection beyond this transaction, I would be like,
Yeah.
Like, what's the limit? Like, how far can you push it? Like, can you go to like
chain introspection. Well, a block header introspection would be really useful for some
That would be
protocols.
super useful. What's that? Yeah.
There has been thought on this, but I have just left that door firmly closed. It's not necessarily that there's not good stuff behind it. It's just that, yeah, there is a whole new universe of problems that I have not thought about.
Yeah, I think most discussion these days is about transaction level introspection, and I haven't really. I don't think that any serious proposal goes beyond that.
So if you want to come to my talk later, there is a fun trick that you can do with Cat to carry state forward where you can kind of look back on the previous transaction. It's expensive, and there are some limits on how much you can do, so it's not infinite. You can't, keep hopping back all the way to Genesis or something, but you can, look at kind of an uncle output in the previous transaction and use that to carry like a state commitment forward. That ends up being really, really useful for like building finite state machines where you want to be able to like choose the tap leaf that you're going to fire based on what a previous state commitment is. It doesn't give you, arbitrary introspection into somebody else's transaction unrelated. I mean, maybe you could do it with like an SPV proof or something, but then you have like SPV assumptions. The thing that I think is worth remembering is that in Bitcoin, we don't have the ability to like write to arbitrary global state in somebody else's transaction. So a lot of the weird, re-entry bugs and other problems that you see in other blockchains are because everybody has, global state that you're able to mutate, and the ordering of that can get bad. So it's still Bitcoin.
All right. Give him a hand.
Thanks, guys.
Thank you guys for coming. I think it was very informative. So, take off my shirt.
Yeah, where's the mud?
Oh, not today.
Yeah. So it's funny. I have part of some script that you can verify SPV. Yeah. And then, but like, what if somebody puts you on a fork?
I talked about it last night.
You can, check that block header is some number of blocks.
Hey guys, just so you know, there's lunch being served out the front in the yellow Penske truck. There is lunch available now. We are going to start back up at 1:30. Check, check. Hey, 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 hey. Yeah, much better.
Hey? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Is it good? Yeah, they can't really read this, can they? I don't know. Can I? The code? Oh yeah, that's better. It's good. Yeah. I can do it. That's fine. All right. Are we ready? Okay. Okay, I was told to introduce myself, so I'll do that. I'm Johan. I work at Nightig doing open source work, and I'm going to present to you something I've been working on, and I'm going to explain what it is. So we call it optimistic execution of RISC-V and verified in TypeScript. And this is obviously part of the covenant discussion, since this all gets possible as an effect of having covenants available in Bitcoin script. Okay, so what is this optimistic execution of RISC-V in TypeScript? It's a proof of concept we built. It's working. We have code running right now, so you can play around with it. Optimistic execution means, I'm going to go into it, but this is kind of built on the Merklei's all the things proposal by Salvatore, and it's about getting better and more expressive smart contracts into Bitcoin without increasing the on-chain footprint. So this is what I'm going to go through. I'm going to just tell you a bit about the terms I'm using in this talk. I'm going to tell you about what features and what we get from having this available on Bitcoin. I'm going to do a technical deep dive where I'm going to go from end to end, where you start with like a high-level language and down to the Bitcoin script at the end. Then I'm going to do a demo and take a brief look into the future. So what is optimistic execution? Optimistic execution means that we want to perform as much as possible of the computation off-chain and only perform it on-chain if we have to. And if the incentives are aligned, then we expect the on-chain footprint to, or never actually get into the worst case, because it will be expensive for those trying to cheat in this game. So in the best case, we are only putting the input to the program we're running on-chain, since that is data that has to be available for everybody verifying the program. So that has to go on-chain. And I'm saying that in the worst case, you only need a smallish proof to go on-chain. And that's it. I'm saying it's smallish because it's very, very small compared to the actual computation, but it's larger than the best case. RISC-V, what is that? It's a reduced instruction set architecture. And the nice thing about it is that it's fairly simple. So since we're emulating all of this in Bitcoin script, we need to be able to actually express what the RISC-V architecture is doing in Bitcoin script. It's also getting a lot of traction, so it has a lot of compilers, tooling, things you can use when you are building programs using RISC-V. However, we can basically use any like high-level language that has a RISC-V compiler when writing these Bitcoin contracts. The limitations, however, are that it has to be deterministic, since everybody needs to be able to verify the computation and get to the same result. We need to make sure that computation is always deterministic. That means like things like no concurrency, no operating system calls, nothing like that. But usually that's fine. You can use a language like Rust or C or a lot of other languages. So what's Merklei's all the things, or MAT in short? It was a proposal by Salvatore made in 2022, I think. It's a fraud-proof framework, meaning that it's, as I mentioned, it's optimistic. You only like put this real proofs on chain if you catch someone cheating. It's called Merklei's all the things because we Merkleize the script, the program itself. We have like this compiled program. We Merkleize it in effect of having it being Merkleized in the taproot tree. We also take the memory of the computer we're emulating. We're Merkleizing the full memory and only committing the state root to an actual Bitcoin transaction. And this is very powerful, but it gives you a lot of memory to play with. You can have gigabytes of memory, and you only put this hash, the state root of the memory, on chain. Finally, we Merkleized the computational trace. So in case somebody's cheating, we ask them to prove or to show us the computation it did. So we go through the computation, Merkleize the states, all the states in the computation, and we Merkleize that again, and put the state or the computational trace root on chain. To enable math, it has an accompanying opcode that was also mentioned during the panel called check contract verify. It's very simple, which is also why I like it. You just check that the input key has some internal key and is tweaked with some data, and also that it's tweaked with some taproot. And you can do the same with the output key. And that way you can take the state from the input, modify it somehow, and then commit it to in the output. In addition, we use cat a lot because we're working with Merkle trees. So cat is very, very useful in that regards. So what does this give us? Well, it lets us developers write Bitcoin contracts in higher level languages. Bitcoin script is much like assembly, and if the vast majority of software developers these days, they don't ever have to deal with assembly code. So why do Bitcoin developers still need to deal with assembly code? So if you have this full suite of tools where we can write high-level languages and compile it down to Bitcoin script, I think that would be very helpful in getting more developers working on Bitcoin scripting. Since it's optimistic, all the execution is happening off-chain. That means you get a very, very small on-chain footprint, which is nice from a chain and fee perspective. I listed some use cases here. There are probably many more. One of the most sought after that I know is like shared UTXO schemes, where you can have like contracts, payment pools, vault type constructions, where many users are sharing a UTXO on-chain, and they have like their off-chain rules about who is owed what from the UTXO. So you can build that. You can also use it as a building blocks to build bridges for sidechains and rollups. And you can also optimistically create CK verifiers using this framework, which is again a building block that you can use for a lot of other interesting stuff. Okay, so let's do a technical deep dive. I'm gonna start from see this from like a developer's perspective. If he wants to write some contract using this framework, I'm gonna go step by step. How do we go from the high-level language to what we put on chain? So we start out with a high-level language which has compiler support for RISC-V. Here's an example of a Rust program that you can do. This one will just read some integer from standard input. This is what's going to be put on chain when you are kind of like emulating that you're running this thing on chain. You're going to do some computation using this, and then you're going to write the output to standard output again. So it's much like writing a regular command line tool, really. And that was also what we tried to achieve with this. So the result you're writing here, it can be simple. It can be like a true-false statement telling you whether you're able to claim the money. Or if we have like amount introspection, you can say that this is the value you're able to like take out of the contract, for example. When that is done, we build it, and we target like a 32-bit RISC-V bare metal target that doesn't have a lot of features, but it doesn't have a standard library. It doesn't have like operating system underneath it, but it has what we need. And that gives you a binary. And this is a RISC-V binary that you can disassemble and look at the opcodes or whatever the CPU would run when it runs this binary. And and this is what we use to convert or to actually create the Bitcoin scripts. So we're going to just have a program, go through every opcode in the RISC-V binary, look at it, and then create an accompanying Bitcoin script that does the same as this one opcode is doing on the CPU. And in effect, like every script we're creating is basically doing the same thing. Luckily, RISC-V is fairly simple. So as an example here, we're looking at the add operation. It takes whatever is in a register, adds, in this case, 256 to it, and then stores it back into another, or in this case, the same register, but it could be any register. So this is basically what every opcode does. It takes some value in a register, does something with it, write it back into another register. So in this case, was that a block? Oh, let's do this. Yeah, so basically we have this memory root, which we fetch from the input of the transaction. In this case, I've highlighted like the program counter register and the A0 register. The script is going to validate first. So the runner of this, or the creator of this transaction has to provide a witness, telling you something about the memory. So you're going to put like the value found in A0. It's going to put also add a Merkle proof to this value. And the script, the first thing the script is going to do is check that this value is correct. It's going to take the input memory, or the state root to the input memory. It's going to check that this Merkle proof is valid for this value of A0. Then it's going to add 256 to it. We also increment the program counter. That's something we do for every script. And then we're going to take these two new values together with the Merkle proofs we have already. We're building a new Merkle root, and then we take that Merkle root and check that that's the same one as is committed to in the output. And this is how we validate every state transition of the VM. When that is done, we're going to take all the scripts for all those lines in the assembly file, and then we're going to add them as scripts in a tap tree. Then we're going to assemble the tap tree, and that's what goes on-chain. Now, when this contract output is on-chain, anybody can claim it or try to claim it. So in this case, let's say Bob tries to spend this output. In order to do that, he has to like provide some input and output to the program. So he says like, this is my input. When I run this, I'll get this output. Somebody challenge me if I'm wrong. In order to disincentivize actually trying this with invalid data, we also make him like add a collateral input to this transaction. And there's a time lock on the output, giving anybody time to verify this data and try to challenge him if there's something wrong. And that's the nice thing here, right? Since the input is valid or is in plain text in the input, in the witness, anybody that knows what this program is doing under the hood can try to run it with this input and check whether the output is correct. So let's say Alice looks at this and figures out, oh, Bob is actually not entitled to this money. He ran it with some input, but the output is wrong. He claimed it was something else. Then Alice will challenge Bob. And she does that by spending his output before the time lock expires. Again, we want her to have some skin in the game, so she'll add some collateral as well in order to not challenge something that's actually correct. And when Alice challenges Bob, that means Bob has to show Alice how he got to this result. So again, we'll post a Merkle root in the witness for Bob, and the Merkle root is a Merkle root to the computational trace that Bob performed. So this is something you may be familiar with, but you have this trace, and for every state, you you like say, this is my starting state and this is my ending state when performing some kind of operation, and then you build a Merkle tree such that you can bisect down to this state. And this is the next part of the protocol, the trace bisection protocol. Since Alice knew the initial state of the memory, and she has the input, she can run the whole thing and figure out that, at some point, the trace I get and the one that Bob put on chain, they diverge. So at some point, there has to be Bob was doing something wrong. So she'll play this challenge response game where she asks him to reveal sub-trees in the trace, and finally, you get down to the state where they disagree. And when you get to this state I, where they did agree, and in state I+1, in this case, they don't agree. And here is where this script we just created in the beginning comes in. So Bob is required to run this script, and if he's able to provide a witness to the script such that he can take the state from state I to state I+1, then he actually performed the computation correctly. And he can burn Alice collateral, since she tried to challenge him even though he did it correctly. And if he can't do it, then after a time lock, then Alice can actually roll back the whole output into the contract output again. So Alice can't take the money here because she's just challenging him. So she's kind of rolling back the contract back to before Bob was trying to claim the money, and also burning Bob's collateral in the process. Okay, so I'll do a brief demo if we can see my screen. Yeah, so the nice thing about having a RISC-V being our compile target is that you can use a lot of high-level languages. So in this case, you'll see a Rust program where we have defined some boilerplate. So there's some assembly setting up everything and calling into this, calling into this run contract method. So what we're going to do in this case, just as an example of something that's not very complex, but still not easy to do in regular Bitcoin script today, we're going to do some division. So here, we're going to read something from standard input. This is it's being put on chain. We're going to just check that it's not a trivial factor. And then we're going to take this number, 901, divided by the input, and check whether the input was a factor of this number. And then we're going to write 1. In the other cases, we're going to write 0 to the output. This means essentially that if you know the factors of 901, then you're able to claim the money in this contract. If not, you shouldn't be able to. Then we'll just, can you see this? Yeah, so we're using a regular Rust compiler for this. So we have the target set to 32-bit bare metal RISC-V CPU. We can build this and get an ELF binary. Then I have this tool called ELF trace, which will actually trace this binary. So what it will do is exactly what I showed. It will take the ELF binary. It will go step by step in the assembly code. It will create a Bitcoin script, write that to file, and in the end, when you have all the scripts, you'll assemble them into a taproot. And in addition, you can give it an input and an output. And in that case, it will run the full program with that input, and then create the computational trace as well, and use that to create the witnesses. Yeah, so I prepared a simple one here, just for you to see how it looks like, if you can see this though. So this is the add This is like a script for doing the add operation we saw earlier. It takes like something that's in the register, adds a constant to it, and then stores it back into the register. So I won't go through the script. It's pretty crazy. We're doing a lot of cats. So what it's doing here is like since we don't have 32-bit unsigned addition in Bitcoin, this is actually doing like it's doing 32-bit additions using bits here. So it will and actually build the memory representation here, and then do the Merkle proof, and check the Merkle proof against here, and then we'll actually start. Okay, yeah, now it's checking the Merkle root, and then it's going to actually start doing the addition. Yeah, something like, yeah, and so forth. You can fast forward this, and it's verified. Okay, so that was the demo. Maybe not the most exciting contract, but you can write basically any Rust program, right? And that's one of the things that's cool with this. If you have a Rust compiler, then you can tap into like the big ecosystem of Rust programs and libraries that are out there. So what I was able to do last week was to compile the Rust library Winterfell, which is a CK library, using this framework. And that's nice. I have it here. Let's see. Yeah, so the nice thing about it is that as long as the library you're using is not using the standard library, which is not supported at least currently, then you can just import it. You can write your program, take some input, run it on this library, and then output whatever. And then you compile it, and then you run it on elftrace. Elftrace just runs it on a virtual machine and creates the traces. In this case, though, it is fairly slow because it's a very large program. We can start running it here. Let's see. If I have the right command. Yeah, it's this one. I had to skip checking because it's too slow. So this will create like a 3 billion state trace. So it's very slow, but that's fine because we assemble everything into Taproot, and if you put the time locks, you're generous with the time locks on chain, then it's no problem people running this thing. It can take hours, right? Doesn't matter because you have time to respond to if somebody is doing this incorrectly. Yeah, 500,000 different scripts that goes into the Taproot tree in this case. So I'm not gonna go let this finish because it's gonna take a while. But that's the idea, that you can tap into the different libraries that's out there, and then you can run this heavy computation off chain. But the only thing that goes on chain in the optimistic case, or in the best case, is the input to the program. So in this case, it's the CK proof itself. You need to put on chain. With the example I'm compiling here with like a Fibonacci proof, it's about 2 kilobytes. And you can imagine other, maybe snarks or other proof systems are optimized for smaller proofs. So that's what could be best for our case. Yeah, if you want to see more of this and play around with it, here's some links. Also toward the end there, where I showed the actual script that runs in this case. It's a tool I created called TapSim. So check that out if you want to play around with Bitcoin scripts. It's a TapScript debugger basically, which I found useful. So any questions? If I got time left. Yes. Yeah. Yes, I commit the input, and so so there's different stages here. One is the fraud proof challenge. In that case, it's the trace that's committed to. That's used to actually be able to, like, if you told me this was the trace before this transaction, then you have to be consistent and give me the same or this a subtree. It doesn't have to be. Only the input needs to be. And if you give me some input and I say, oh, the computation with this input is wrong, then give me a trace. And that trace has to be consistent with that input. Yes. Yeah, you need the full trace yourself, or you need a trace, a correct trace. No. So as the spender, you only publish the trace root of your trace. I'm as a verifier, I create my own trace and create my root. And if that's different, then I know that you're lying. Yeah. Okay. You know the full program, you know the input, and from there, since it's deterministic, you can generate it yourself.
Gotcha. That makes sense. All right, I'll ask one more question, then everyone else can go. But I have more later. But you mentioned like collateral, right? So do you have a system to basically determine like how much collateral should be put up for a particular program, or is that just sort of like hand wave? People will figure out what that value should be.
Hand wave, yeah.
Okay.
Yeah. It's up to the whatever contract you're making, I guess.
Gotcha. Okay.
Yeah, a question back there first.
Yeah, so is the verification happening as part of consensus, as part of this op CCV?
Yes, so op CCV is just checking that the input and the output to the transaction, like the key, the taproot key in the input and the taproot key in the output, is consistent with the Merkle roots we're giving it. So it's very simple. It's just check that the key is tweaked with something.
Okay, but so there still needs to be, so if there is fraud that occurs, then there still needs to be a justice transaction. Is that correct?
Well, it's just in the sense, what I'm saying here is like they have some collateral, they have some skin in the game. So if I catch you cheating, then I'll burn that collateral.
Okay, and how many, can you do that in one transaction, or is that going to take multiple transactions?
You need to go through this fraud proof challenge, which is
it similar
logarithmic
to
in the number of state transitions.
Okay.
Do you know like Arbitrium, like the OG version, or even like TrueBit? It's similar to that.
Okay, I'm going to have to look that up. But
a question here?
This will be like a game. We can just pass it.
So is it possible that for a given input, the smart contract can be written so that the steps in the smart contract itself are different, so that the traces would be different, but they get the same output?
Well, yeah, so it has to be deterministic. So if I'm not cheating, and even though we get to the same output, if we disagree of how you get there, then I can challenge you and, well, if you're able to prove that your trace is correct, then it doesn't matter. But you need to be careful there. I think if it's not deterministic, then it's not possible to make statements about whether a root is correct or not. So, yeah, I don't think you can have non-determinism in there.
So, at the end you showed like the WinterFlow program that was like, much larger. So one question is like, at least with your current implementation on your laptop, like, do you have a metric of like opcodes per second, or like cycles per second, in terms of like how fast the emulation is to generate the trace? And I mean, like
the VM, the trace itself.
Yeah.
I haven't measured that.
Yeah, that'd be just an interesting metric because, like, for example, people like RISC-0, they have like a kilohertz, megahertz metric that they look at, but that's like with the optimized GPU thing.
This is based on the RISC-0 VM.
Yeah. I mean, the interesting thing about this that like all of this looks like Starks without privacy, basically. Like you have a trace, you make a Merkle over the trace and so forth, but Starks add privacy, which is the heavy machinery, you can say.
So it's basically what we do. We do use the RISC-0 library, which they have a VM for making CK proofs over the computational trace. So we just like cut that short. We just run run it with the RISC-0 VM, the CK VM, and then before we start creating the CK proofs over the trace, we just take the trace and Merkleize it. So that's what we do. So it should be faster than that, at least.
Sure, yeah, you don't need that.
We don't need the CK part.
Probably a stupid question, but can you talk a little bit more about burning the collateral? And like, is that like sending the Bitcoin to an unspendable output or something, or just talk about the mechanic and kind of
what I do is just like put it to
seizing?
fees. Put it to fees.
Yeah.
I think you should just, well, if you had amount introspection, you could probably do like very interesting things with the collateral. It makes it maybe part of the, maybe Alice gets part of it. If you catch Bob cheating, has an incentive there. It's just, yeah, I think it's up to whoever's writing the contract, and with tools like amount introspection, you can do whatever you want.
Cool, thank you.
Well, yeah.
All right,
Okay,
I have my last question. What was the like cumulative size of the ad script that you had there? So you had the initial script, that was, or no, it was division basically. So like if you sum all of the tap leaves up, the ones that weren't published on chain, what's the size of that?
Oh, yeah.
Because I saw you're saying that you did bit composition for the addition, which is obviously
Yeah.
more expensive than doing the opcodes. Just curious about like what the raw size of the sum of all the leaves is.
Yeah, so in this case, I think the addition script is here. It's about 2 kilobytes. So remember, this is very naive. This is just me doing like bit addition. So this is one of the larger opcodes because you actually have to do this 32-bit arithmetics. I tried to do the multiplication as well, but that one became larger than the 10 kilobyte limit on the script. So I just like changed to a compiler target that doesn't have multiplication, so I don't have to deal with it.
But I guess you could do like a continuation like that too, right? In terms of like, I guess like checkpoint the state and then resume it in another script to get around that 10K limit, or?
Yeah, maybe like you can do it like on the compiler stage.
Yeah, that's effectively what Zero does as well in order to do recursive proofs in their system. So maybe there's something you could take from there as well.
Or maybe you can just do a 8-bit target or something.
Yeah. Small numbers.
It doesn't really matter how long the trace is because you're going to Merkleize it, so it's going to be a small one chain anyway. Back there. Last one, I guess.
So this is kind of an open-ended question that I like to ask. So if you were a dictator of Bitcoin for a day.
Just for a day?
Just for a day. It's all you really need, actually. What kind of, like, how would you implement this in a more efficient manner?
I guess to be a nice guy, I wouldn't change Bitcoin in a day. I would propose something and then let the community decide that. No, I think,
humble.
I think I would like just a bunch of introspection opcodes and EC operations, so I could like check tweaks and check build tap trees and whatever I want to do in script.
Okay, so more introspection.
More introspection, yeah. Oh yeah. So the thing here is that this is a 32-bit unsigned target, so I need to be able to do like 32-bit unsigned adds, but Bitcoin script only has 31-bit. So I had 1 bit too little, so I had to re-implement everything in order to make it work. So better arithmetics would be very useful to just cut down the size of the scripts. All right, thanks.
flipping over? Yeah, I think it worked. Am I in the wrong hat? I don't know if we want to get the lights on. Do you want to turn on the lights? We can like wake people up. There's going to be a lot of math in this talk, so I don't know if we want the lights off. I don't know. I don't know when you want it. Yeah, I think it's up there. Yep, that's it. Is it time to start or? Yeah? Okay, cool. Hey everybody, thanks for coming. My name's Randall. I'm from Taproot Wizards, here to talk about inscriptions. Just kidding. We are here to talk about building covenants with OpCat, also known as BIP 420. You know, that's the wrong link. It is BIP 420. So, actually, yeah, that's right. You know, eventually consistent systems are funny like that. So what I want to do today is, we've heard a lot today and probably in other discourse that you can use OpCat to build covenants. This is all based on some work that, what is up with the lights? Yeah. Oh, okay, I gotcha. You know, we'll just plow on. Yeah, that sounds great. Yeah, pay a higher fee. So this idea that you can build covenants using OpCat is based on some work that Andrew Polstra did in, I think, 2021. But a lot of people, even if they read that blog post, don't really understand what it is or how it works, mechanically how it works. That's led to a lot of people assuming that you can do things with OpCat-based covenants that maybe you can't, or that you can't do things that you can. So what I want to do today is to walk you through how you actually use OpCat with Schnorr signatures to build covenants in Bitcoin. And the goal is not to go through like a full enumeration of everything that you can do. It's to give you some understanding of how this works mechanically, like what you would actually have to do in your program and in script in order to build a covenant this way, so that you can get some intuition. Like the goal here is that if you're thinking about a problem that you're trying to solve and you want to know if you could solve this problem with a cat-based covenant, I want you to have sort of a jumping off point to understand the kind of physics of this. And then we'll talk a little bit about some other opcodes that might be useful, and we'll look at some examples of how you can do this. So we're going to talk about two things. Mostly, we're going to talk about OpCat, and we're going to talk about Schnorr signatures. This is the really short slide before we get into how Schnorr signatures work. OpCat, super simple opcode. We take two elements on top of the stack. We concatenate them, and they go back on the stack. So you take A and B, cat them together, and you get AB as a single element. Schnorr signatures, and specifically Schnorr signatures as specified in BIP 340, which is what we have in Taproot. We're going to walk through how Schnorr signatures work. We're going to touch on how verification works, and then we're going to show how you can kind of abuse a Schnorr signature to make a covenant. So a signature is a pair, R and S, and you can imagine having like a sign API or a sign method that takes in a message, a private key, and a nonce, which is like a one-time value that you never want to repeat. And it's going to return this pair of values, R, which is a point, and S, which is a scalar, just a number. And does everybody know what G is in SecP 256K1? G? OK. So the way that we do key derivation for elliptic curves is there's this special point on the curve that we use in Bitcoin called G. It's the generator point. And the idea is that by adding G to itself over and over again, you can generate all the valid elements of this group. And so the way that we turn a private key into a public key is we multiply your private key times this generator point, and that gets you a public key. We do the exact same thing for your nonce, and that gets you this R value, which is the public nonce commitment. And then what we do is we construct what's called a tagged hash. So we want to make sure that if you construct a signature in kind of one context, that can't be replayed in a different one. So we put this tag, this little bit of context, inside of hashes when we're doing things in Taproot. And so you take your public nonce commitment, which is sort of like the pub key version of a nonce. You take the public nonce commitment R, the public key, and the message that you're signing over, make a tagged hash out of that, multiply it by the private key, and then add the nonce. And then these two values, your public nonce commitment R and this tagged hash that you've created S, these are S times D plus K. These two things are your actual signatures. When you look on chain and you see a 64-byte Schnorr signature, like this is actually what it is. And then I'll just go through this really, really quickly. It's a lot of math on the screen, but I just want you to be convinced that it works. The way that signature verification works for Schnorr signatures is you basically reconstruct that tagged hash. That's this E value on the second line. And then we're going to check that R equals S times G minus E times P. And what you're basically doing is you're reconstructing this challenge, and then you're multiplying it by public information that you have, and if it matches the R value that's committed in the signature, then it's a valid transaction, or it's a valid signature. So we're going to dig into what's actually in this signature that lets us build covenants. So again, the second component of a signature, this S value, contains the public nonce commitment, a pub key, and this message. And I've just been saying message over and over again, not saying what it is. This is like the thing that you want to sign. So in BIP 341, which is like script and signature validation rules for Taproot, we have a common signature message. So whenever you sign over a Taproot Bitcoin transaction, there's a standard set of fields that get concatenated and hashed together in order to construct this message. So, and all of those things put together are at most 206 bytes. So this is my horrible drawing of a Bitcoin transaction. These are the normal components that you think about when you think about like what things are committed to in a transaction ID. So you've got your inputs, which are like a prev out. You have a transaction ID and a index. And then you've got your outputs, which are an amount and a script pub key. And you've got a version and a lock time. We also commit to some other additional information in this common signature message. We get the index of the input that we're spending from. We get amount, script pub key, and sequence numbers for all of our inputs. And then that saxophone in the bottom is meant to represent the annex. Nobody knows what the annex is, so it's a saxophone. So if you go and read BIP 341, this is actually all the fields that get committed to in this common signature message. I'm not going to read all of them, but some things to draw your attention to are that we have a lot of information about our inputs. So we don't just have the prev out. We don't just have the prior transaction ID and index. We actually have amounts. We have script pub keys. We have sequence numbers. We have some extra information if we're doing like an anyone can pay. So there's actually a lot of information in here that gets committed to when you sign a Taproot transaction. So that is what goes into this, this message here. And the hack, the thing that lets us do covenants here, is if you take this S value, which is this tagged hash, and you set D, which again is the private key, to 1, and you set the nonce to 1, then the R value, which is your public nonce commitment, this is K times G, is just going to be G. It's this generator point. It's a well-known thing. It's part of the definition of the group that we're working over. And then if you set your private key to 1, then the public key is G. So we end up with the S value for our signature is just this tagged hash of G concatenated with the message, which again commits to all the information in our transaction, times 1 plus 1. You can get rid of the times 1. And what you end up with is you can construct this Schnorr signature that just is basically your message hash with some copies of G plus 1. And this is a valid Schnorr signature for the private key 1 and the nonce 1. So what you can do with this is if you can actually build this signature on the stack or get this signature on the stack somehow and then call checksig, then if that checksig succeeds, then it means that the message inside of that signature matches what's actually in the transaction. So the values that you committed to in that message field must match the values of this transaction that we're inside of, otherwise checksig would fail. So this is how we actually do covenants with cat. So we're going to walk through what that actually means in practice. How do you actually use this? So what we do if we want to make a covenant is, and the value here is that we get introspection. Johan was just talking about it's great if you can get introspection. If you want to be able to work with components of your transaction in your Bitcoin script, so you want to be able to introspect a input amount or an output value or an output script pub key, what you're going to do is you're going to take the elements that you want to be fixed, so you want to send to a specific script pub key, and you're going to either embed those in your script or somehow copy them into your script. And then all the free values that can vary depending on spend time constraints, you pass as witness data. And you use all of that to construct a BIP341 signature message on the stack. So again, here's a subset of all these elements. You take them, commit to the ones that you want to commit to, and then the rest of them you pass as witness data. And if there's some tricks here where if we don't actually care about specific values, like maybe you don't actually need to introspect any of the inputs, you just need them to be there for the message to be valid, you can actually just pass the commitments and save on some cats and some hashing. And then you take each of these components, you cat them all together, and then you hash them to get a commitment. You cat all of the commitments together, and now you have a BIP341 common signature message. So as an example, here's a bunch of these fields that need to be signed over in order to be a valid Taproot Schnorr signature. You take all of these, you call cat over and over and over again. You get this thing, which is just all of them catted together. And then you hash it, and you get a signature message. Build a signature around that, and you're good to go. So we construct this signature message on the stack. We prepend it with some copies of G for our public nonce commitment and our pub key. We add on that tag for the hash. We saw that there was like a BIP340 challenge tag. And then we hash the whole thing, add another copy of G, and we have almost a valid Schnorr signature. Because if you remember, we don't end up with just this hash value. We actually need hash value plus 1. Thank you, 31-bit unsigned arithmetic. We don't actually have U256 arithmetic in Bitcoin script yet. Script restoration coming soon. So what we do instead is outside of the script in our application, we grind fields until the signature ends in a 0. So you got to pick a field in your transaction that you can just grind through. I've found that nlock time and sequence numbers work really, really well. On average, you do less than 256 times. And then you lop off the last byte of the signature, and that's what you stick in witness data. So you have the first 63 bytes of a signature, put that in a witness, and then in your script, you add on a 0 byte, use equal verify to check that it matches the thing that you computed, and then you add a 0.1 onto the end of it and use that to actually do the checksig. So this first one is used to validate that you computed everything the way you wanted to, and then the second one is actually enforcing the covenant. So that's a lot. Sounds like a lot of steps. Tried to unpack it and make sure that it kind of stood on its own if you read the slides later. But the overview of this technique is you take the values that you want to enforce in your script. So this might be input amounts, it might be input sequence numbers, script pub keys, whatever. You fix those in your script. And then at spend time, and this is something that your wallet would do or your application software would do, you build up your transaction in memory. You grab all of those other values that aren't committed to in your script, and you pass them in as witness data. And then on your script, you cat and SHA all of them together to get this S value, and then you do check sig. And if it holds, then your fixed value is what's actually on chain, which is pretty great. So now we have covenants. We did it. We can all go home. So some things that we can cover are on the input side. We can cover prevouts. We can cover input script pub keys, which is surprisingly useful. We can cover input amounts, sequence numbers, and then you can tell which input you are. So you can say, this script must be in the first input, for example. And then on the output side, it's kind of normal output stuff. You get a script pub key and an amount. Some things that we could do with that, just as an example, are you could say all the data that I'm going to shove into the witness is going to be everything except for the destination. I'm going to fix that in my script. It's actually going to be committed to in a tap leaf. And I build up my signature. As I'm building up this common signature message, when I get to the output value, instead of pulling it from the witness stack, or pulling it from witness data, it's just already there in my script. So I build up the signature around this pre-committed value. And then if you validate the signature, then it means that coins are going to that destination. So this is a way that you can do kind of like an enforced output. If you want to say my coins can only go to this address or that address, you can actually enforce that with opcat. Some other little toy examples. In addition to fully specifying an output, kind of CTV style, where you specify both the destination, address, and the amount, you can actually mix and match. You could say for the first output, I want to go to a specific address, but any amount. And then the second output, I want to be a dust value, but it can go to any address. And you can mix and match these things depending on your application. Another example that you could do is you can take the output destination address, the script pub key, make a copy of it, and then use that copy when you build up the commitment on your inputs. And this is actually a way that you can enforce that the coins are being spent from an address back to the same address. So you can actually have covenants where the coins have to be spent back to the same address over and over again until there's some state transition and they can escape. And we'll look at an example of that now. So if you wanted to build a vault, I think vaults are kind of the stereotypical covenant use case because they're actually useful and you can generalize them in fun ways. What you want to have is you want to have a construction where you send coins into a vault, and then the only valid spend from that vault is to trigger a withdrawal. And when you trigger the withdrawal, you want to specify where the coins are ultimately going, and you want that specification to be binding. You don't want somebody to be able to change their mind later. And then after some time lock, the coins can be spent to their final destination, or at any time before they're completed, they can be swept back to the vault. So this is kind of a state machine that you get. And this gives you what people call reactive security, where you say, I've got my coins in the vault. When I want to withdraw them, I trigger that withdrawal. If I don't go and hit the big red button in 2 weeks, then my coins move on to where I was withdrawing them to. But if it's not me withdrawing my coins, if it's somebody who stole my keys, then I push a button and I sweep my coins back to the vault. This is like a really nice kind of basic reactive security setup that we could do in a couple different ways, but we'll see what it looks like in CAT. And just to number these, I'm calling this kind of trigger transaction 1, and then the recovery sweep is 2, and then the completion is number 3. So tricky thing, we don't have the ability to do a tap, tweak, verify in Bitcoin script. So you can't tell right now that a script pub key commits to a particular tap tree. So the way that you need to implement multi-step state machines using opcat is by having each of the different state transitions that can happen be different tap leaves. and then having the contract send coins back to itself, but using different tap scripts depending on when they are. So in our construction, we have this like contract address for your vault, and there's a trigger script that sends things back to the contract address. There's a cancel script that sends things back to the contract address, and there's a completion script that sends things to the target that you committed to when you did the trigger. So trigger is pretty easy. What we want to do is assert that the script's input is the first input, that like you're in the right spot. You're going to assert that the amount paid in on the first input matches the amount paid out on the first output. So if you have a 1 Bitcoin UTXO, you are spending one Bitcoin towards the trigger. We're going to assert that the first input script pub key matches the first output script pub key. So we're asserting that you're sending back to yourself. And then we're letting the second output be any script pub key. And this is actually how we designate the target. So we're saying, this second output is where I want my coins to go. And if you kind of imagine this as being the transaction graph, this transaction on the left is this trigger where we're sending coins kind of towards the withdrawal. And the second output, we're kind of just using to hold a little commitment to an address that we're going to use later. And if you take a Bitcoin transaction and you take the version field, serialized inputs, serialized outputs, and the lock time, and you hash all of them together twice, you'll get a transaction ID. And one of the fields that gets committed to in the BIP 341 signature message is the input prev outs, which include a transaction ID. So what we can do is we can actually take all of the fields for this serialized transaction and put them as witness data into our completion script, validate that second output, and then hash it all together and assert that that transaction ID matches the transaction ID in our input prev out. So this gives us the ability not just to introspect our transaction, but we're now actually introspecting an output on the previous transaction. And this is actually a way that we can carry state forward in sort of a multi-transaction state machine, because you can have outputs that carry commitments or state roots or addresses or whatever they are, and then in a future transaction, you can validate that that output belonged to a transaction that fed the transaction that I'm in. So this is actually how we can do kind of cross-transaction introspection. So the way that works is we take all this previous transaction data in the witness, make a copy of that second output script pub key, the little picture there, and then we construct that TXID and assert that the prev out TXID matches. And now we have this script pub key that we know was spent in the previous transaction, and we can use that to assert that our output matches. So we can assert that we are sending coins to an address that we previously committed to. And then add a plain old CSV relative time lock, and we've got vaults. And then cancellation is really boring. You just make sure that the script input is the first one, and you make sure that the amounts match and that the script pub keys match. So this is our vault. Oop, there we go. So this is our vault, really basic state machine. You have coins, you start withdrawing them, and when you start withdrawing them, you commit to some amount of state. And then after a time lock, you're able to withdraw your coins that's contingent on that previously set state, but you have this cancellation path, and this cancellation path sends the coins back into the vault. And there's actually like a really interesting way that we can generalize this shape of a state machine beyond vaults. Because we can say, all right, what other things can we do where from a given state, we want to be able to go to specific outputs or specific shapes of transactions, and we want to let the next step, the next set of allowed state transitions to be contingent on the shape of a previous transaction. And we have the ability to carry a little bit of state with us, and we can dispatch to other state machines. We can do some really interesting stuff with this. One of them is, instead of this cancellation step just sending stuff immediately back to the vault, maybe this cancellation step actually sends you to another state machine that does a more complex conflict resolution. And in this conflict resolution step, if somebody wins, then you kind of go back to the trigger state and you're waiting on a time lock. And if somebody loses, then you just revault the coins. This is like a generalized version of a vault. And if you were in the room, I don't know, half an hour ago for Johan's talk, you heard him talking about Matt. If you didn't see that, you should go and watch the recording later. It was awesome. You should also check out Salvatore's talk, I think tomorrow, about Matt. Friday, okay, Friday. And also check out the website, merkle.fun. Matt is a generalized challenge response protocol for doing optimistic verification of arbitrary off-chain computation. So you should watch Johan's talk. It's way better than my slides. But the idea is that you take some arbitrary program trace and you can take that trace, Merkleize it, and then add commitments for sort of the state of the system before and after each subtree, and then you can drive a interactive challenge response protocol between the challenger and the withdrawer where they take turns opening Merkle commitments until they find the program step where they disagree, and then you actually execute that program step on chain. And you either get an equivocation and somebody wins, or you get a timeout and it, they get their coins back. So you can take this interactive challenge response game that lets you do optimistic verification of arbitrary off-chain computation and just sort of sub it in the cancellation path of our vault state machine. And now you have a method where you can say the coins in the vault are encumbered by arbitrary off-chain computation. Somebody can optimistically try to spend them, and then if somebody calls foul and issues a fraud proof, then you go through an interactive, multi-transaction process to actually resolve whether or not it was a valid fraud proof or if you're allowed to take the coins out. We thought this was a good idea. People write white papers. We thought that was boring, so we made an illustrated children's book. It's called Cat VM, There and Back Again. You should read it. It's great. The protagonist is visited by the spirit of Satoshi and has to help people get off-chain where riches and adventure awaits. It's a lot of fun. I think you should read it. And we're trying to actually build this into a system that people can build real bridges and real contracting systems on top of. We call it Cat VM. It's kind of a cheeky name. It's basically Matt, but it only takes dependency on opcat. So it doesn't require additional covenant opcodes. The only thing that it needs beyond what we have today is opcat. So if we have opcat, we can build this optimistic withdrawal system where funds are handled by arbitrary off-chain computation. Anybody can initiate a withdrawal or a challenge if you have enough data to reconstruct all the trees. So it doesn't rely on having like a predefined set of people that you've done like pre-signed transactions over. All of these script commitments that you have to do can be computed kind of once per program and then just like kept in your client software. And you should definitely check out Salvatore's talk to learn more about it and Johan's talk. Some other upgrades that would be super, super nice for this, check contract verify or some other tweak add would be great. Check sig from stack. If I was Bitcoin king for a day, we'd have a ZKP verify, like no question, and we'd also do script restoration. It would be awesome. If you want to learn more about this, I think the best place to start is Andrew Polstra's Cat and Schnorr Tricks. There's 2 blog posts, read them. A lot of people have misunderstood them, so this talk probably made that worse, but maybe it made it a little bit better. There's also an implementation of all this. So we wrote a vault using opcat. It runs on regtest on your machine. It takes 3 commands to run, and you get a fully fleshed out vault that you can do withdrawals, you can steal, you can cancel, whole thing on regtest on your machine. It's called Perfect Vault. It's with cats. And then if you want to read the Cat VM book, it's at catvm.org. It is a great children's book that has a lot of good information about covenants and Merkle trees. If you read it to your children, I recommend a booming voice for the spirit of Satoshi. And that's it. Thank you so much. That was like half an hour. I'm happy to take questions over beers later. Oh, Lalu. Yep.
Test.
Oh, sure. I'm happy to.
Oh, should I go? Or
Yep. It'll switch over in a second.
Okay, I don't know if I should wait or not. Given that you're constructing the SIG hash, on the stack basically, and the SIG hash, like you're saying, includes like, the like pre-input pre-fashionings things like that as well, which scales the number of inputs. Like, do you do anything to get around like the stack limit? Because at a certain point, you only have the 520 byte, chunks basically, right?
Yep.
And I guess are you like how you're incrementally hashing that together, or
yeah. So like for each of the commitments that go into this message. So the max size of the final message when you're done is like 206 bytes because it's a bunch of commitments that are all catted together. So each of those commitments, like you have a single commitment for all of the input script hub keys. So you take all the input script hub keys, cat them together, and then hash it. So you have a single 32-byte hash, and that's like your input script hub key commitment.
Yeah.
Where you can run into trouble is if you have lots and lots of outputs or inputs, then you won't be able to build that commitment. I found in practice when I was doing the vault, when we've been doing some cat VM stuff, we've been doing some also fun little like game things with cat. In practice, like you don't end up with giant transactions for sort of like the middle of your state machine. You might have like a giant transaction like funding the initial contract, but if you're not trying to introspect those things sort of on the way in, then it's okay. Where you're more likely to run into the 520 byte limit is actually when you're doing this like state passing trick, you have to pass in the full like serialized transaction. So like all the inputs, all the outputs. And so if that's a big transaction, you can run into that limit. The limit that I ran into first was there's a relay policy limit on the maximum witness item size of like 80 bytes. So for this serialized transaction, you have to pass it in as pieces and then cat it together.
Gotcha. No, yeah, that makes a lot of sense because, like, pre-seg wit, you actually hash an entire transaction.
Yeah.
But then, in order to fix the quadratic,
yeah, so you don't have to pass witness
data
data in, which is great. Yeah, you're just doing input and output serialization.
Cool. And then the other question I had is like, you're saying that you're going to basically pass like the free elements as like witness elements, right? But it feels like maybe that's a foot gun because otherwise, like that opens you up to basically malleability, right? So imagine if you had like a script that was like op if check sig and then else something else. Someone could potentially modify one of those free elements basically to have an invalid state, which would cause you to go to a different branch. I feel like that would be only bad like if you had unconditional branching basically versus acceptance or not. But that's just like one thing that popped into mind. And like, malleability is a concern here if you're passing things to the witness, but maybe in the future, if you had checkers from stack, you could have those be signed. And then at least that's some authentication, but maybe it doesn't solve all. But it's potential
right
foot gun for architecture or for something like this.
Yeah, you can't do any like authentication over the elements. You're really just doing like assertion against like the structure of the transaction. It's like something that we're playing with. There's been some really interesting. There was a Delving Bitcoin post. Lalu and I were talking about this. So I'm saying this for the benefit of everyone, right? But so there's a really great Delving Bitcoin response where somebody took Alloy, which is like a model checker, and they like modeled out this construction, and they found like a bunch of issues, and like we've been talking about it. And so like these things are complicated. It's nice that you can do. That you can kind of mix and match which things you want to have commitments over, and you can do that with like a really low-level building block. But I do think what we're going to need if people want to use this stuff at scale is really good tooling for like authoring these contracts and for analyzing these contracts. I've been having a lot of conversations with people about building like a builder abstraction where you have a bunch of gadgets. So you say like, I have the input introspection gadget, I have the output introspection gadget, and you just say like, I've got a builder, I want to add these gadgets, and it builds up the script, and it also builds up the requirements for what witness data needs to be passed in. Because depending on which things you're introspecting, you might be able to save some bytes with like, you're going to be checking that an input address and an output address match, so you should like copy that instead of passing it twice. And there's some kind of like, if we know the pre and post conditions for like what things need to go on the witness, then we can glue them together the right way. But it's a lot of work.
Yeah, looking forward to playing with that tool more. Or I'm working on a little demo myself
Yeah,
too.
I don't want to say it's like a mini script, but it's it's something like that. It's a Bitcoin tooling joke. If you guys don't laugh, I'm going to start telling algebra jokes. What's purple and commutes? And a belly and grape. Okay. Yeah. Yeah. So I don't think I put it in the slides, but it's in the code, and you can go run the code. So the trigger state requires, I'm trying to remember how it works. It's based on the number of inputs and outputs, and it constrains the number of, it constrains one of them. I don't remember, but there's a way to do it. Yeah. Sorry. Yeah, I haven't looked at that code in a couple weeks, so I don't remember. But it works. Anybody else? Cool. Feel free later. Coffee, beer. Happy to talk about cats. Thanks.
A big thank you to I think everyone's favorite shitcoin, Arindal. Up next we have Nifty to talk about SIG-Ops. Nifty.
Wait, I thought it was SIG-Oops.
SIG-Oops?
Well, all right. We're running a little behind. Sorry about that. Oh no, it's okay. My from all right. All right. Alrighty. Okay, we're running a little behind, but I think that's okay. I'm going to go ahead and hit share on my slideshow presentation. Not that one. Skip. No. Slideshow. Cool. All right. How many of you have heard of SIG-Ops before? This is okay, pretty much everyone. All right, maybe this will just be a quick review for most people. But maybe not. All right. So does anyone know what this is a picture of? A signature, right? Okay. And so like this is a normal signature, but Bitcoin transactions also have signatures in them, right? So a Bitcoin transaction has a signature on it. Sometimes those transactions have more than one signature on them. Sometimes they have a lot of signatures on them, right? So you have a Bitcoin transaction, you have some number of signatures on your Bitcoin transaction. Most Bitcoin transactions have at least one signature on them unless you're a degen who's trying to get a mint ahead of everyone else and trying to optimize on the amount of weight you're putting in your transaction, and you're hoping that the amount of fee you're paying / the obscurity of what you're doing will protect you from getting sniped in the mempool. Okay, that's this whole side story. We're not talking about that. But most transactions have a signature on them. So in this talk, I want to talk about something called SIG-Ops, more like SIG-Oops. Cool. A little bit about me. My name is Nifty. I also go by Lisa. I am a block streamer, longtime Core Lightning contributor. I started a education project called Base 58, School of Engineering, a few years ago, and I ran Bitcoin++. Also some interesting background. If you know what ISIG is, I'm an ISIGer, and I am a not graduate from the Ricker Center in New York City. Kind of like a lot of stuff. Cool. But let's talk about SIG-Ops. So what is SIG-Ops short for? It stands for Signature Operations. What does a signature operation looks like? This is the most basic kind of signature operation you can do, which is you have a pub key and you call op check sig in it, right? So any kind of op code in a Bitcoin script that is invoking a signature operation is called a signature operation. Hopefully that makes sense. Cool. Okay, so what are all the SIG operations that exist in Bitcoin script? Well, there's the plain opcheck sig. There's also its favorite cousin, opcheck sig verify. We have opcheck multisig and then opcheck multisig verify in general. These are all of the, let's say, okay, yeah. So these are most of the signature opcodes that we've got. And so you have a signature in a transaction, you're going to have a pub key, and then you're going to call opcheck sig to verify if that signature is actually valid for the transaction given the pub key, et cetera, right? So that's a signature operation. And again, op-check multisig is just like a normal signature operation, with the difference that instead of checking one signature, you're usually checking a lot of different signatures. Cool. Okay, so the number of signature operations, or number of times that you have to verify that a signature is correct, is a signature operation, etc. Okay, so this is like a concept. Why do we bring this up? Okay, because in Bitcoin, we kind of have this accounting that we do around the number of signature operations that happen in a transaction, or more generally, as we'll see, in a block. And so there's kind of these rules around like counting SIG-ops is sort of a thing that we do. So there's kind of, I went through a Stack Overflow post, so there's a Stack Overflow post that had some interesting, I don't know, so there's just kind of some clips from it because I thought it was a good explanation. So like if you have a check sig or a check sig verify, you count that as one SIG-op, generally speaking. So this would be 1, right? And then if you have a op check multisig, well, this is clearly more than one signature. How many signatures, how many should you count for this, right? It's one opcode, but it's going to have more than one signature. So calling it just one wouldn't work very well. So there's some special rules about how many that counts for as your signature operations. I think in older scripts, they just count it as a flat 20. It's kind of like has a generic cost of 20. But in more recent things, it counts the number of public keys that are listed in the signature operation up to 16. And if you go over 16, you're in the 20 bucket again, which I think is kind of funny. I don't know. Like if you put 18 in there, it's actually going to cost you 20. So maybe you shouldn't do that. I don't know. Anyways, cool. Okay, so op-check multisig, we have a different way of counting the number of signature operations that this opcode is going to make happen inside your computer, right? Cool. And the reason, okay, so anyways, we're still going through the accounting version of this. And then, so those are kind of the numbers, 1 and 20, if you're doing before SegWit happened. And then SegWit happened, and we had to multiply everything by 4 because we multiplied weights by 4. So now we're also multiplying signature operations by 4. So if you're using a pre-SegWit transaction script, you're going to multiply everything by 4. So now if you have an op check sig, it's going to be worth 4. It's going to count as 4. Again, this is like weird accounting. I don't know. These are accounting rules. These are the rules. This is how it is. I don't know why it's like this. So if you're doing a sig-op, a signature operation, not in a taproot script, not a non-SegWit script, it's going to count for 4. And then op check multisig is going to count for 80. Is everyone following? Got like numbers. We're adding things up. You count how many opcodes are in a script. And then why does that matter? So you get a number at the end of the day. You count up how many SIG-ops happened in a transaction. It matters because there's a rule, a consensus level rule at the block level, where you can only have 80,000 SIG-ops in a single block. I didn't have time to look into exactly, apparently there's some more relay level rules. So there's kind of 2 layers of rules in Bitcoin. There's one that's like, I've made a block and it has to follow a set of rules so that other nodes will take my block. We call those consensus rules. There's another set of rules that are, I would say, almost like transaction relay rules. I think the more general term people use for that is policy, which is I have a transaction, and in order to send it to the next person, it has to follow a different set of rules. Those are policy rules. I think there's different policy rules around SIG-ops. Again, I didn't look them up exactly, so I apologize for not having exact information on that. But the consensus level rule is that if you have a block, all the transactions inside of it, all of the signature operations inside the transactions inside of a block, count them all up using this accounting method that we just went through. You can't go over 80,000. Is everyone following along? Makes sense. Okay, we got a SIG-ops limit. Here's some fun kind of like side facts about SIG-ops. If you have an if, else, and if statement, and I put, I don't have a slide for this, but if I put inside of here, can you see my cursor? Yeah. What if inside of here I had like an op check multisig? Let's just say that counts as like 20 for simplicity's sake. And then let's say I had an op check sig in this else branch. So it's an op if and op else. Are both of these branches going to execute ever? No, right? Only one. Only the op check multisig on the top that you can't see that I'm just waving in, or the one on the check sig on the second else branch is going to execute. If Bitcoin looks at this script, how much is it going to say how much is this going to count against my SigOps budget, as they call it, like 80,000 is their total budget. How many is this altogether going to count against it? Is it going to count 1 or is it going to count 20? Anyone know? Who thinks it's going to be 1? Who thinks it's going to be 20? Who thinks it's none of the above, it's actually 21? Okay, the answer is it's 21, and the reason that it's 21 is that Bitcoin doesn't look at, whenever it's going through and it's counting the number of SigOps that happen in a transaction, it doesn't pay attention to branches. It just counts the appearance of every SigOp in a script, if that makes sense. So if you take a script and you know what the opcode hex number is for a signature operation, it scans through the script, it ignores everything else, and it just counts up how many of them and does some accounting on that, if that makes sense. So you could have more SigOps in a script that never get executed that would still count against your budget, which is kind of interesting. Okay, I have one more maybe trick question about SIG operations. How many SigOps does check sig add count for? How many people have seen this opcode before? People are like, I know what that is. There's like a handful of people. Okay, so not a lot. So okay, this is a new script opcode that got added for TapScript, otherwise known as SegWit v1 scripts, and there's a rule according to the Stack Overflow post I read, which I'm assuming is right because Peter Willow wrote it, I think. Taproot scripts don't have SigOp counts. So according to this post I read, you should be able to use check sig add as many times as you want without it counting against your SigOps limit, is my understanding. I should verify this, but there's question marks there. Cool. So okay, so we had some trivia things, right? So in pay to taproot scripts, SigOps are not counted. Cool. Okay, so the SigOps limit made the news last April 1st. And no, I don't believe it was a joke, because a big mining pool didn't make a mistake once. They made a mistake twice. And the mistake that they made, the sig oops, so to speak, that happened, is that, oh no, wait, sorry, this is just a graph of all the SIG operations in blocks. This guy, 0xb10c, does some really great kind of miner level analysis. So he has an analysis here of, if you look at every block that's been mined in the last, I don't know, 130,000 blocks. No, that's math. Anyways, if you look at a bunch of blocks that have been mined, then you kind of graph how many SIG operations were inside of each block. You can see that for most blocks, the majority of blocks that come through the system, the SIG ops limits is unimportant, right? They don't get anywhere close to this line, which is the limit. So for most miners, when they're building blocks, they're looking through all the different transactions that they could put into a block. They're picking them based on, I don't know, favorite child, amount of fees that you're paying them, bribes that you paid out of bound, whatever. While they're doing that, majority of the time, they don't have to worry about how many signature operations are inside those transactions. They can just put it in a block and move on with their life. It's not a problem. Every once in a while, we get really close to the limit. But in fact, back in April, this is from April 20, this is from last year. So April 1st, 2023, F2Pool mined a block. So they mined actually 2 blocks in April that they mined where they got bad block SigOps, too many SigOps. So they had 2 blocks that got mined where they took transactions and they did a bad accounting job and they went over the SigOps limit and then they found a winning nonce for that block. So they found a winning block. And then once they had that winning block, they started telling everyone, hey, we just won a block, you know how blocks get propagated across the network. But as that block went to every other node on the network, they rejected it because they're like, no, this has too many SigOps in it. We don't want it. So basically, if you're a miner, that means you lost out on revenue of 2 blocks that would have generally been yours, except you failed one of the, I would say, fairly obscure consensus rules. Cool. Okay. So why do we care? Why are we talking about SigOps? Why is this an interesting thing to cover at a Bitcoin script conference? I think that they're really interesting from a perspective of, where did this come from? Why do we have them? Where did it get introduced? I think, I could be wrong about this, back in 2010, so very early, Bitcoin history, they found transactions with a ton of op-check sig commands. And what this was doing is, it was every node, when it gets an op-check sig transaction, like a transaction with an op-check sig inside of it, it has to do work to verify that that signature is correct. So having a lot of signature checks inside a transaction means that every node on the network has to run that many signature checks before it can say, okay, this is a good block or this is a good transaction. So in some ways, SigOps is one of the few places in Bitcoin today that we have limits placed on the amount of execution that's allowed inside of Bitcoin script. So I don't know if it was exactly related to this problem that they then added the SigOps limit. So like, you can only do so many signatures in a block, and that's a way to prevent people from creating transactions that basically make too much computation happen across the network whenever those transactions get sent out, and basically clogs down every single Bitcoin node because they're sitting there calculating transaction signatures for minutes at a time because they have too many of them. So coming up with this 80,000 limit was, I believe, 20,000 limit, which then later became 80,000 when SegWit hit. I believe was a little arbitrary. I don't know, source needed on this. But the idea behind the SigOps limit is that we want to prevent, or we want to place some sort of reasonable limits on the amount of computation that a Bitcoin script can cause other nodes on the network to do, right? And the reason for that is that that's costly, right? It doesn't cost you, it costs your node time and energy to process and to run these verification checks, right? Because Bitcoin is a don't trust verify network that's distributed, so every single node on the network has to run these verifications independently. So adding a lot of computation to a Bitcoin script means that you kind of create the cost on the network to verify transactions, et cetera, which is costly in the long run. Kind of a bad joke that it's like making your nodes do proof of work also. No, okay, cool. So again, execution costs of Bitcoin script are a real thing that in general we kind of have hand-waved over traditionally the cost of, and had just like, okay, there's like a limit on how many there can be, and that's just like a hard line in the sand, and that's how we will generally avoid these problems with the amount of execution that's happening. There's a few other places that you kind of have limits like this that sort of indicate similar things. It's not just the SigOp limit. There's also a non-push op limit in a script, which means you just count the number of operations that happen. It can't go over 201. But I think so it just counts. Fun kind of side fact is this also counts the pub keys and multisegs. So those count toward an opcode limit. Anyways. How much execution you're doing, like there's a few limits on it. It's most of a count-based thing though. So how many operations are you doing? Let's count them. You can't do more than this number, hand wave. Cool. So why am I bringing this up at a script conference? It's because I think that as we start thinking about new scripts and new sorts of execution that we want to ask our nodes to do when we're considering new opcode proposals, I think it's interesting to ask about the amount of computation that each of those opcodes is going to be adding to the system, and maybe it's an opportunity for us to reconsider the costing function that we have for what a signature for what a operation costs, right? Right now, some of the most costly things are signature verification operations, but if we add something like check sig from stack, will that count towards the SigOp limits? I think there's like some interesting questions there, again, around accounting of new scripts, etc. I think we all heard from Rusty earlier this morning, who had a really great presentation, or I think ideas about more in-depth ways to kind of do this costing of how much it costs to actually execute different scripts. That might be one possible way that we could move forward with how we're going to add or bring back new opcodes, et cetera, and make sure that we're kind of keeping our limits on the CPU of nodes on the network in check. Cool. Okay, I think that's everything that I have. I don't know how I'm on time. I have two things to show you on before I go. The first one is that I want to talk, I run this school called Base 58. I talk about Bitcoin engineering and protocol things. So you thought this was fun. class will be even more fun. We do hands-on stuff, and I explain how things in the protocol work. I have Udemy classes online, and I'm hoping, fingers crossed, when I get some time next week to finally get some more online classes out and available. I think we're doing a wallets class at the end of this month online. So if you want to learn about how hierarchical deterministic wallets work, we're going to talk about pub keys. I think we're going to do PSBTs. And yeah, that should be the thing. Maybe we'll talk about, I don't know if we'll talk about miniscript. That's a hand wave, maybe. And then the last thing is, if you learned, maybe hopefully you picked up some things today that might be useful for trivia. Base 58 is hoping a trivia tomorrow night over at the Bitcoin Commons in conjunction with Austin Bit Devs. So if you're around on Thursday and want to come try your luck with some friends at how much you know about how Bitcoin script, etc. works, come hang out on Thursday. Cool. Okay. I don't know if I have any time for questions or not. Are we good on time? I have 4 minutes. Okay, so maybe 2 questions if there are any. If not, we've got snack break, etc. before coming back for more talks. So great. Okay. Thanks, Gal. Yeah. What other obscure consensus rules? Your brain's like, I don't know. I honestly think this is one of the most obscure, weird consensus rules. And the way that I kind of found out about it was because of these bad blocks, if that makes sense, last year. Because all of a sudden there was news. It was news. It didn't used to be news. Yeah. The question, maybe I did. I don't remember if I repeated the question. Okay. But it was, yeah. Anyway, sorry. Yeah. So the answer has to do with something called the Coinbase transaction, which is the transaction that miners put together. And the default block template, starts getting into things I'm not like super the most expert at, but my understanding is that in general, if you're using Bitcoin Core, it reserves 100 SIGOPS for the Coinbase transaction. So when you're building a block, you're putting transaction into it, you have to add a special transaction kind of at the top of the heap called the Coinbase. And Bitcoin Core kind of has some automated stuff to do this for you, and it just leaves 100 SIGOPS for the Coinbase, period. My understanding is that F2 Pool had written a custom block building like template where they were no longer reserving 100 SIGOPS for that. They were reserving like 1 or 3 or some like tiny number, and they miscalculated how much they had left off for themselves or something and went over. So that's which twice, and then they fixed it. I assume, one presumes they fixed it, yeah. The Stack Overflow post that I read, which is clearly correct, like I did not verify, I apologize. Oh. I think Andrew might be able to answer this for us. Okay. I'll repeat it, yeah. So what Andrew was explaining is when they were designing TapScript, which was what that so what we're referring to is my slide where I had check sig add, which is a TapScript only opcode. So one of the problems with this SIGOPS stuff is that whenever you're creating a cost for a transaction, you're usually counting the number of bytes in the transaction, right? And you pay based on the number of bytes in the transaction. The SIGOPS limit is like a separate requirement for a kind of a constraint on what transactions are allowed to go inside a block. So suddenly you have the kind of a 2-dimensional optimization problem, is what Andrew was saying. Andrew, I think I'm doing, yeah, okay. And the problem is that now you have, you kind of have to get less SIGOPS, but more bytes, whatever. So they tried to unify both of them for the taproot, and the way that they did that is for every SIGOPS, you must have at least 50 bytes of weight. So rather than looking at the SIGOPS limit, you now say, okay, so you kind of like get rid of the limit of SIGOPS. You're not counting SIGOPS anymore. You're just saying every SIGOPS appearance in a script must have 50 bytes of weight that you're paying for in the general transaction. So it changes it from this weird accounting thing to this opcode has a weight requirement of the rest of the transaction. And I think that's pretty easy to hit if you have a signature, because you usually, most signatures are 64 bytes. So is that right? Yeah, I think signature is 64 bytes in Taproot. So if you have a 50 byte requirement along with a signature operation, like you're always, by definition, if you're providing a signature, you're always going to go over the limit. And some of the ways that TapScript scripts are now constructed, you could wait, but what about the slide about the op-else stuff, right? That could get you in trouble because you wouldn't provide a signature for an op check sig and an if branch, right? So if you're still counting those as 50 byte weight, then you might still run into problems. I think the way that you would solve that is in TapScript. The way that the Merkle roots are constructed, you're generally going to, the way the Merkle roots are constructed, you're generally probably not going to be having if statements in scripts anymore, because you're able to do more complicated tweaking of exactly which script you want to reveal. And so hopefully with all these things together, you would really never run into a situation where you have more signature operations than bytes, I think. Cool. Okay, I think I'm definitely over time now. Thanks, everyone. Please enjoy your coffee. Yeah, thanks.
when should I start, or should we wait for more people to come in? I don't know, scheduling. Cool. I'll wait for. I think we're good. Hello. I can. Cool. No. It works. I can see it here. It's great. But you guys cannot yet? Okay, now you can. Thanks. Okay. So this is going to be a quick technical overview of some new Covenant opcodes that I recently proposed. I have a bib for them, but I know people don't like to write bibs, so the title of this was kind of like TXHash TLDR for those that don't want to read the bib. So it's a proposal for 2 new Covenant opcodes, maybe 3 new Covenant opcodes. We'll see that in the end of the talk. So who am I? I was just in the next room, so I'm not going to say it all again. I was at Liquid, Rose Bitcoin, and also working on ARC. So I'm going to start with a brief history of this proposal, because it's not really my idea. It was proposed originally in the mailing list by Russell O'Connor as a general idea, like, hey, we can do maybe this. And then for a long time, nothing really happened. And then I thought it was a good idea, and I kind of formalized it in a bib and implemented it in a few places. And now I'm mostly waiting for feedback, which in the last, since it's been out for 6 months, hasn't really come too much. I know some people in here actually left comments, but there was very few. So I'm here basically asking for feedback, because this is all mostly my work, and obviously a single engineer makes a lot of mistakes. So the idea is actually a variant of the Covenant proposal. Most of us know CTV, check template verify, which is kind of like a way to do pre-signed transactions, but without the signatures, right? So you basically specify an entire transaction, almost everything about the transaction, and you're gonna kind of commit to that as if it was pre-signed, but without the signature on it. Kinda, because there's a few things more you can do that signatures currently can't. So it's kind of this idea of predetermined transactions. So the entire transaction is fixed, and you commit to that the transaction beforehand. And the nice thing about CTV is the code is really simple, right? It's basically a single hash that you commit to. You calculate it like this, and then you check if that hash actually matches the thing that's on the stack, and that's how you commit to the transaction. So that's really nice. But it's also very limiting. So TXHash is a generalization of the CTV concept. So instead of only being able to commit to exactly this set of things, like in CTV, you can actually choose pick and match or whatever the things that you want to actually commit to in the transaction, and the things that you want to leave free for the protocol to fill in later on. So in order to pick the things that you want to commit, we introduce this concept called a TX field selector. So it's, like the name says, a way to select the fields from the transaction that you're interested in. So the proposal actually introduces 2 new opcodes. One of them is going to be TypeScript only, TXHash, and you basically give it a field selector, and then it pushes the actual hash that it calculates based on the fields you selected and puts it on the stack. The other one is check TXHash which is basically another way to do this, but is compatible with SegWit v0 and Legacy, where you take the hash and the field selector of the stack, then calculate the hash and make sure that the hash is the same as what the user inputted. So TXHash verify looks very much like CTV, but with extra flags, and TXHash gives you like a way to play with this thing on the stack later on. Yeah, so this is how it works, right? So you pass the field selector in TXHash and you get the hash, or you pass the hash plus the field selector into this and it says yes or no. So okay, so how does the field selector work? So this is kind of a diagram that I made of like everything about a transaction that could possibly be interesting, and then the bits that are committing to them. I'm going over them one by one, right? So we have 16 bits that we want to like get everything into. So we're going to start with the version and the log time, which are like global fields, obviously useful. Then there's a few fields that are related to the execution of the script, not necessarily the transaction, but they're useful because in all of the signature hashes, they're also committed to, and they are useful to like control what's actually happening in your script in the context of your transaction. So it's like the current input index, the control block, which holds like the mass tree, so like all the scripts, then the explicit spend script, which is very useful in like SegWit and SegWit v0 and legacy contexts. The last script, opcode separator, no one knows why, but it's everywhere in all the SIG hashes, so we also have it. There's one bit we're not using currently, then the control bit I'll come to back later, and then you have some fields of the inputs. We have the prevouts, which commit to the previous transaction. We have the sequence numbers. We have the script sigs. They're currently usually empty, but you never know. We might give them some meaning some point. Then from the previous UTXO that you are spending, you can actually commit to the script pub key and the value. We're also including the annexes because they're obviously going to have some meaning at some point, right? I mean, we have them. And then on the output side, it's a lot simpler, just script pub key and value. And this is how we, like, you input these 2 bytes, you have the 16 bits, and setting the bits to 1 or 0, you can actually commit to these fields individually. And then there's multiple inputs and multiple outputs, so then additionally to those 2 bytes, you also have a way to specify which of the inputs specifically you're interested in and which of the outputs specifically you're interested in. So first of all, you can commit to the number of inputs of outputs if you want. Like, is there 4 and I want the first 3 or something, right? So you want to know how many there are, or you don't. Then there's 3 special cases we define. So either you don't want any, but maybe you want the total number of them, or you want all, or you want the current, right? They sound a lot like the SIG hash flags, like all, non, and single. Then you also have the option to pick like a prefix, like the first n, right? This can go up to 8,000. So you can say the first whatever. And then you can even pick individual ones. So you can say the first, the 8th, and the 9th. And you can do this with absolute indices and relative indices. So you can say the one before me, the one after me, the one 8,000 after me. These numbers are just because the number of bits we have free. Those limits. I don't know if you even can have 16,000 upwards, but so the nice thing that this proposal has, it's actually very compatible with CTV, because we define an empty field selector. Like if it's 0 bytes long, we actually pick a field selector that is equivalent, more or less, not byte for byte, but equivalent to CTV. It commits to the same things. We call this the template default, and then we add one extra default. That is the all case, which is useful if you would ever use this for signatures, and it basically commits to everything. I'm currently working with Brandon to maybe add a whole bunch of more like special cases, because we would like to have more usage of single byte field selectors instead of 3 to 4 or 5, 6 bytes field selectors. But currently in the spec we have just the template one and the all one, but we're trying to optimize it a little bit. So not only can you use this to commit beforehand on something that your transaction could look like, but if we have something like checksig from stack, you can actually use this hash as as a super like pimped version of a SIG hash, because we have currently 3 SIG hash modes. We have none, single, and all, and then we have the anyone can spend flag, where you can like play a little bit with what you commit to. But with this, you can actually use this as a SIG hash flag and like commit to anything you want. So it's basically a SIG hash, basically whatever goes into the SIG hash, into the signature, similarly. So if you have check from stack, you can do a signature TXHash. Oh, here I missed the field selector, sorry. Can you see the cursor? Here needs to be the field selector first. But you can get the hash and then check the signature over that hash from the stack. So obviously you have SIG hash all, that's why we include all. And then you have template, which kind of behaves more or less like APO. Probably people are going to say no, but like it's kind of similar to useful to APO. That's how people with like L-enhanced wants to do APO style things with CTV and check from stack. And this can basically do anything like other SIG hash proposals that have been made, like SIG hash group. With TXHash, you can do all those things because you can pick any of the outputs and inputs that you want. So it's very important when you do SIG hashes that like you commit also to what you have committed, so that people cannot like swap things around, like, oh, you committed to the first input, but then actually you use it as an output, right? So the control bit that we saw before, you use a control bit to specify, I also want to commit to the field selector itself. And another cool thing that we heard about today that this could enable is stacking. This morning, Rusty talked about stacking, and TXHash actually enables stacking automatically, because you can say, everyone has a certain number of inputs and outputs, and you can just say, I'm committing to my input and my output, and then using a way where you provide a whole lot of different signatures based on where in the configuration you are, and then some coordinator can take all the signatures, pick the right one based on how the transaction actually looks, and then you can make one big transaction where a lot of different people have actually committed to just their share of it, and then the coordinator can put a fee on the bottom and then broadcast it. So you use the individual selection mode for this. The way you would do this is that the first input commits to all your output, and then the other inputs would just commit to the previous input to also be there to make the scheme efficient. And then you provide a lot of different SIGs, and then the coordinator puts them together to like make sure that the configuration just works out. So probably like you're gonna say like I have 2 input 3 outputs, so I'm gonna like say I want the 2 at the same height, and then the other one I just sign 1,000 times like +1 +2 +3 +4, and then the coordinator can just like pick the right one. It's a bit of an inefficient way to do stacking, but since this is all off chain, doesn't really matter too much. It's like you want to sign just your part in the transaction, and then someone can take all these parts, make a single transaction, and then stick the fee at the bottom, like stack all the bundles together, and then stick a fee at the bottom and broadcast it, right? So you want to have a transaction with 2 inputs, 3 outputs. Instead of making a transaction, you just make like a bundle and you sign only for your stuff. You send it to me, and then other people also send this to me. I bundle this all together because you're only committing to your stuff, and then I commit to everything, and I add the fee, right? And the nice thing about this is that it's not miners doing this. Anyone can do this, any random operator. And the actual fee still gets paid. Well, the actual fee still gets paid over the normal mempool, and you don't have to be a miner to do this. Like any wallet can do this. Any question? That's a good question. That's a good question. Exactly. Yeah, so even if you're not stacking, one of the main benefits, I don't have this in my slide, one of the main benefits of TXHash over, for example, CTV, is that you can just say, I have 2 inputs, 3 outputs, I commit to all that, but I leave space for even myself to just add fees, right? So with CTV, you need to commit to everything up front. So you don't know how much fee you're going to have to pay because you don't know the fee rate. So what usually you would do in any construction using CTV is you leave an anchor output that then you're going to spend later on. So you're going to first broadcast this with the anchor output, spend the anchor output, and then pay the fees from the child using child pays for parent. But with TXHash, you can just make the signatures only commit to the things that's important, and then you can put your own input, adding your own input and your own output, and pay the fee later on. So that's a way how you could do it for yourself, but then actually with stacking, you can get all of those bundled together.
The way that I've always thought about it, maybe it's basically redoing the SIG hash system, right? Like the SIG hashes tell you which bits you're signing
Yeah, exactly. Yeah, yeah, exactly. So the SIG hashes are very useful for anything like order matching and this like distributed order book kind of things where like I have my stuff that I care about and like I just want to make sure that I receive something from someone in return for something that I sent, right? You can do all of these things using this as a SIG hash. So the main concern that comes up when talking about this is quadratic hashing, right? So what if a transaction is really big and you can just put this field selector on the stack, call TXHash, and you're going to have to hash like thousands of bytes because like you're actually referring to some things in different previous transactions. So all this output can be really big, your script sigs can be really big, everything can be really big. And if you're always going to hash this, you could actually get like what they say quadratic hashing, because then for every input you need to hash all those things, so it's like n squared, and then you need to hash a lot of things. So one of the main like technical challenges in this proposal is how to avoid this quadratic hashing exploit. But we have a way now, it's implemented and described in the bib using the reference implementation, where you don't have this problem. What we're doing is we have a lot of caching at different levels. So first of all, we're going to cache all the variable-sized fields. That's kind of similar to what the SIG hash does, but then individual. So all the fields that can be of any size, we're going to hash them at most once, which means that if someone tried to exploit and like get the same fields multiple times in a row, all the variable-sized fields will always be just 32 bytes because they're already hashed. And it means that for every transaction, you're going to hash those at most once. And that's kind of amortized, like that's how the SIG hashes also do it. Every time, any transaction, you just pre-calculate all those hashes. For the SIG hash, this can be done lazy. So every of those items you only hash once. And then after you have hashed all the big items once, then the amount of data you're going to hash for each invocation has really clear bounds, because the amount of inputs you can select is bounded. And then also for the leading, I don't know if I have this here, for the leading thing where you like say the first n, we're going to also keep a cache where every interval, like every 10 for example, you keep the intermediate cache, so that if someone asks for the first 90 and then asks for the first 92 and then for the first 93, you keep the hash of the 90, and you know you're going to always only at most have to add 9 of them, right? Because you keep a cache for the 90, for the 100. So if someone asks 96, you're going to have to hash 6 more of those values, but it's always bounded by 10. So we're going to also incur a cost for this opcode, just like checksig costs you 50 validation budget. I recently bumped it from 15 to 25. I might change my mind again and bump it back to 15. But if we get this great script restoration, we're going to probably use the Varos budget for this, which makes more sense than just picking a random number like we're doing it right now. But there obviously needs to be some cost associated with this. I thought it was fair to have half of the checksig, because like with a checksig you kind of do this as well, and then you do EC. And it turns out they're kind of almost equal for like slightly larger amounts of bytes. So like, yeah, you get a budget, and if you do this like a lot of times, you're just gonna run out of budget. So what's the status of this? I recently got a bib number, thank you. The bib has been written. It has a reference implementation and some test vectors. I say maybe test vectors because it's quite rudimentary. There need to be a lot more edge case test vectors. So this needs a lot of review. There's an implementation in Bitcoin Core and Inquisition that also needs a lot of review. There's also an implementation of the caching in Rust Bitcoin. Kind of also needs review, but it's like not as important. Please review the other things. And then one last thing I want to talk about. So like we defined this field selector, right? We defined a logical way to point at things in a transaction, and that's kind of useful. And another way we can use this for maybe is with another opcode, maybe optx, which I think originally was proposed by Rusty in some mailing list posts, which basically means you take, do I have it? So you take the field selector from the stack, and then instead of hashing all the things that the user pointed at together, you basically put them on the stack, right? And then the control bit that we were using for the hash to include the field selector, we can actually repurpose this bit to let the user choose between wanting to put all the fields on the stack together or all the fields individually. And this way we get direct introspection opcode, where, for example, if you want to look at the sum of all your output values, for example, you could use the field selector to point at all the output values, get them all on the stack, add them together, and then know the total output value, something like that. So this is useful if you want to do math on amounts, or if you want to look inside the scripts that people are using in the outputs or on the inputs. So that's something that is not in the bib, but is something that we could be doing. And then one last thing I want to mention is if the TX field selector actually gets some use, and we notice that it's useful because it's like a generalization of anything, APO, any scripts, non-signal, single, whatever. So like everything can be done with the field selector and many things more. So maybe with TXHash group, people come up with nice new things. So in SegWit, in Taproot, it's actually possible to introduce this as a new key type where you can add the field selector as a TXHash flag. Instead of adding 1 byte, you can add any number of bytes depending on what you want to select. And then the signature just checks using the TXHash. So you don't have to use the opcodes, but you can just directly use it as a TXHash. And that's my last slide. So yeah, please review. I go back here. Need review. Thank you. Questions? Yeah.
So where does this sit with like all the other proposals? Like how does it play well with that sort of best case?
Well, it's definitely less popular because otherwise I would have been sitting here this morning. No, I think it's somewhere in the middle. I mean, direct introspection is definitely more useful than this, and CTV is definitely less useful than this. So like, it's kind of like a better version of CTV. It gives you like a lot more things. It's also a lot more code. I think it's sitting in the middle. You can do most of the things with this. The only thing you cannot do without OptX is math on your inputs and outputs, right?
But I'm guessing the main reason you propose TX is just because we don't have a cat. Like what's the reason?
Exactly. I don't know, but I think even if you have only OptX, you also want TXHash because you want to sign over things very easily. Otherwise, if you have to do the hash, like actually exactly like Rusty said in his talk, if you have to do the hashing on the stack with OptX, you're going to like do all the hashing multiple times, and then if you're actually getting a fair budget, you're going to run over this budget very, very easily. So it's very useful that you have a cached version of all this information, and then you can very easily just query it and get the hash. Ha 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 ha. Yeah. Yeah. Yeah, so the programming paradigm with cat is you have the TXHash we have right now. TXHash is kind of like a TXHash, so the TXHash points to a certain number of fields, and then you basically find a way where you can prove that the thing that's on the stack is actually the TXHash, right? And then you're gonna inspect the different parts of this and then assert them. Assert that this is actually equal to this. So what you do with TXHash is like the things you want to be equal to something, you actually put them into this like hash engine. It calculates the hash. You say like, I want the first output to be this script, second output to be this value, whatever. It gives you the hash and the field selector that you actually picked, right? So you pick the fields in the field selector. The whatever engine will give you the hash. You put that in your script, and then the user who wants to spend this actually needs to fulfill these values. And then you check the hash, and then you do that. Yeah. But the open argument is anything not committed to, right? Like you commit to certain things, and everything else can just be, yeah. But that's only in the check TXHash verify case. You can also use it as a TXHash where you basically says TXHash check from stack, and then the user can say, here's my signature, and this is the things that I committed to. So like this signature is valid for any transaction that actually fulfills the things that I want, just like with a TXHash, and then you can do it that way. Yeah, but it came from me and Russell O'Connor. No, I don't know. Yeah, I should do an NFT. No, I don't know. Yeah.
this, or like sort of like something more complex than like base programming, just to get a feel for sort of like the ergonomics of that kind of? Because my understanding is like you have one that's basically no covenants, and you have one that's also based on the liquid opcodes, which is basically the push instead. Did you look at potentially doing, or is it sort of like time, cost, R&D kind of a thing that's there? Because I think that would help to move it forward, basically, perhaps.
Yeah, I think
you could even take Sapio, which Jeremy worked on, perhaps, and like plug this instead of that. But that's an idea.
Well, yeah, that's not something I want to spend time on. But I could. No. The thing with Arc is the current design of Arc, the TXIDs of the leaves need to be fixed. Right, so that's something TXHash doesn't have. Like TXHash lets you commit to certain things you want, but the fact that all the other things can be anything else, it means your TXID is like in no way not possible to know. So for the naive covenant version of Arc, we would really want the TXIDs to stay the same. So we actually are better off with CTV. But the default mode for TXHash is also CTV. So like we could definitely use this instead of CTV. I mean, this is CTV plus whatever. So yeah, I don't think it would be hard to change the implementation and just have a proof of concept version with CTV.
Just a first comment, a not tongue-in-cheek answer to the question, and then a question of my own. I think the answer about like why not this over the others is like. I wanted to see the BIP, and I mean, it was just put up in October, right? Look at the number, it's 346. CTV is BIP 119. I know the numbers don't indicate everything, but I mean, there is a big time scale.
It's older than Cat.
Yeah. Right, exactly. Like, yeah, Cat, I mean, one of the reasons that's getting a lot of excitement now, partly a big marketing budget, but also Cat was in the original Bitcoin. Like, we know exactly what it looks like. It's been well researched. ATX and TXHash was proposed in a mailing list as like a theory that could do a lot of these things. And I would say like one downside, it's not really a downside, but it makes it like require more thought, is it's more complex. I think like one of the original advantages of CTV, I know that when Jeremy was first working on it, was like there's a subset of things that we know we really want to do, and then there's more that we probably want to do, but as you add that complexity, it's harder to evaluate. So let's focus on this really simple thing. I know it's not enough, right? So I think these are all like important things to evaluate when we're thinking about the proposals. This is like strictly more complex, which is part of the argument for it, but it's also like, well, let's wait and see. And one of my questions is kind of related. There's some question too, like it takes slightly more space to do the CTV stuff with TXHash because it's a little bit more open, right?
No. That's one specific purpose of the protocol, is to make it like exactly backwards compatible. So if the field selector is empty, we just pick one that's equal to CTV.
No,
we might come back on that.
Oh, if it's empty, so then it would be this. If it's empty, then it just does CTV.
Yeah.
Right.
You still lose the 1 byte for the empty stack element, maybe.
That's what I thought. It was basically like I remember seeing something, and again, like it's still going through.
Because CTV takes 32 bytes, and we also take 32 bytes. But 32 plus 1, right? Yeah. So it's exactly the same as CTV.
Bitcoiners tend to care a lot about 1 or 2 bytes.
No, it's exactly.
Maybe to our detriment. I'm not saying that's an argument against.
The byte cost is exactly the same as CTV.
Okay.
But we might come back on that because we might want to like have something else for the default one or something like that. But let's see.
Right. I remember that coming up at one point. But again, this has like been.
But like to come back to the things you said earlier, I think this might even be one of the most recently formalized BIP proposals. Like APO is very old, CTV is very old. Volt was slightly before this. TLUV, well, never had a BIP, but like was talked about. Well, no, this was talked about way earlier, but not formalized. And yeah, you're definitely right. Like Cat is like how many lines of codes? One handful. This is this plus another bit of like this, but like CTV is very little code. The code for TXHash, conceptually, you need to think about it because like you need to make sure the hashing all like checks out. The code is quite verbose, right? It's just literally caching for every field, so it's like copy, 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 copy. So like yes, it's a lot of code. It's like 500 lines of code in a file, but it's just like a cache for this field, a cache for that field. So it's like kind of stupid for both code. But yeah, I think the complexity is definitely a reason why people don't want to look at it. I think also a reason why people don't want to review BIPs or code related to covenants is because covenants are controversial, you know, I mean. Like, yeah, I think when I put out the BIP and the implementation, I got more feedback in private messages than on GitHub because people just don't want to be reviewing or be associated with any of these proposals, because if you review it, maybe you're going to be associated thinking, people are going to think you condone this, whatever. I mean, it's all politics, right? And it sucks. But
I mean, the hashing or the caching is an interesting complexity of it that I don't think a lot of people think about. And I think there was that one pseudo bug that was identified in Jeremy's BIP 119 that had something to do around the caching. It was like an edge case that could never be run into, but I think AJ identifying because he was writing out some test fixtures. But it's like, in a lot of these things, that's the most complex part. And because there's more kind of like, you know exactly what you're going to cache with CTV, yeah. That's also a bit that's simpler.
Yeah, I think with CTV, at some point he had singles, so then you can never cache the hashes because you need to leave out. I think the current one, he zeroed it out or something, so you always had to hash a certain number of things again. Yeah.
Thank you. Sorry.
More questions? Otherwise, thank you very much. There's one more question.
Why 25?
25 what? Why 20? I don't know. Like, I think I spoke with Peter Will, and he said a C operation is roughly equivalent to 10,000 bytes of hashing. And 10,000 bytes seems like a reasonable upper bound. I first thought we were never going to hash 10,000 bytes every time, so I put it at 15. But then it's like, well, you can actually make it go a little bit over. Well, maybe not, because the bounds are pretty clear. But why not? I mean, I definitely think we should move more towards the VAROPS model, where it's like an actual reasonable cost and not just like just random, like,
number,
yeah, just throw a number. And it can be 10, 15, 20, 25, I don't know. It needs to be something that's non-zero so that people just don't throw, like,
It should be between 0 and 50, basically, is what we're saying, right?
Well, yeah.
Because 50 is the SIG-op for, normal signatures, right?
Yeah, between 0 and 50, but it's not 0 and it's not the same, right? So, yeah.
That's interesting.
Cool. Last question. Thank you.
Yeah, I'm plugged in. Okay. Good. All right. Thanks. All right. So I'm not in presenter mode, though. Let's see. Yeah, if I do this, so it's showing my notes on the screen.
Extend your desktop.
Oh, I'm not familiar with that. How do I do that? Oh, okay. Display it, right? Okay.
Extend one instead of duplicate. It should be instead of mirror. Click where it says mirror right here.
Oh, okay.
Go use as extended display.
Which one?
Click on
Let's try that again. Does that work? Yeah. Try this again. Do we have to save it? You said uses extended display, right?
I mean, it's obviously showing.
All right. Hello, hello. Who's here for BitVM? It's not BitVM. Sorry, you're out of luck. So I'll be talking about Bolt 12, which is nothing to do with scripts really, although there'll be some hashing involved. This is more of a lightning talk. So maybe a show of hands first. Who's familiar with Bolt 12? Got quite a few actually. All right. So I'm going to kind of go through some of the background of where we came from and why Bolt 12 is important. And then I'm going to dive into some of the technical details. And during that phase of the talk, I would love if you guys kind of make it a little more interactive. And so I'm going to kind of just go through, kind of do a little deeper dive into it than probably what you've seen before. All right. So here we go. So let's talk about cash and its important qualities. So someone could hand over a $20 bill to purchase something at a store, and they don't need to fill out any paperwork or be worried about transactions not going through. There's no third party involved. The transaction is private and secure. As the world has transitioned to digital money, Those essential properties have been lost, however. A lot of people have not recognized this now, but they will in the future. Bitcoin was invented to solve these problems, and along came Lightning to improve Bitcoin's ability to be used in instant payments. So let's look how Lightning is done today. All right, so Bolt 11, I think a lot of people are probably familiar with Bolt 11. This is the predominant protocol for making Lightning payments today. It certainly gets the job done. It's ubiquitous. It's in every wallet. Supports Bolt 11, but there are a number of drawbacks to Bolt 11. So it's pretty optimized for a select use case, a customer paying a merchant. It's invoice-based, enabling one-time payments that do not allow reusable payment IDs. So an invoice cannot be reused, for instance, and there's no human readable names like you might get in like a Cash App or a Venmo, right? So those were some drawbacks to Bolt 11, and along came LNURL. So LNURL solves several problems. Most fundamentally introduced the notion of a web server to issue invoices. So you can get a reusable payment identifier this way. Because of the reliance on a server that can issue a new invoice each time someone wants to pay you. This is great for tips or donations, for instance. You get a QR code, and there's also like LN address, or Lightning address, which has human readable names. So these are all innovations on top of Bolt 11. So LNURL really advanced usability tremendously. However, if we don't advance the current solution, we sort of erode some of the core principles or properties or components of the Bitcoin, one of which is censorship resistance. So by law, servers cannot allow payments from certain jurisdictions in the world. There are privacy concerns, of course, as well. Servers learn who is paying who, the amount, and log all this that information. Even if a company has no ill intentions, it's still a honeypot of information for governments or hackers, and so that's pretty relevant today if you've been following the news. There's also some security concerns with LNURL. Servers issue invoices on behalf of the user, but there's nothing stopping from that server from issuing an invoice that pays someone else, itself, for instance, especially if the server's a third party. Which is kind of pretty prevalent today with usage of LNURL. Or it could just be somewhat surreptitiously, where maybe 1 out of every 100 payments is paid to someone else. So you might not even notice like you're missing payments. You could avoid detection basically. Yes, exactly. So along comes now Bolt 12. So Rusty, I'm not sure if he's in the audience, but Rusty Russell proposed Bolt 12 a number of years back. And this is kind of like bringing back some of these properties that we all know and love about Bitcoin, but unfortunately have been kind of eroded in the sake of usability. So now we're here to do it sort of in a manner that still has superior privacy, censorship resistance, and improved security. All right, so let's get into Bolt 12. So this is where the more technical part of the talk starts. There's a lot of visuals here, and so hopefully it's not too complicated. And if there's any questions, please feel free to shoot a hand up or shout out. All right, so I'm calling this life of an offer. So what is an offer? An offer is like a reusable payment code in the Bolt 12 world. You could think of it as like a precursor to an invoice. So here we have Alice wants to pay Bob for something. Maybe it's a donation, maybe it's for goods. Not really sure at this point. And Bob has an offer. So Bob has constructed this offer in such a way that he's able to receive payments in a pretty secure and privacy-focused way. The offer is communicated just like a Bolt 11 invoice typically is. It's out of band, meaning not on the Lightning Network. So it could be through a text message, it could be in a tweet, it could be an email, it could be just in a QR code that you scan. And one of the one of the things about offers is that they contain something which is sort of annotated on that picture there. It's a blinded path. So it's a way for Alice to basically contact Bob for an invoice without actually knowing Bob's node ID. So if you're familiar with Lightning, if you announce your node, your node has a pub key associated with it. We call a node ID. And if you have a publicly or known node ID and you're being paid, to that node ID, payments can be correlated to you, basically. Everyone may, or an observer, I should say, may be able to see like who's paying you. So Lightning has today has great sender privacy, but not great receiver privacy. So Bolt 12 aims to I guess fix that. Yes. So there's no limit, but there's a restriction in your QR code. So if you're using a QR code to communicate the offer to someone, then if their camera and their phone, for instance, isn't good enough to scan it if it's a huge size. Exactly. Yes, exactly. But you could use text message. You could tweet about it. Even the specification of offers gives a way to concatenate parts of an offer together using, I think, a plus sign. So if you want to break it across a bunch of tweets and you have a donation address. But yeah, we'll get into the blinded paths in a bit, but there are some more concerns about the availability of blinded paths as time goes on, because these are long-lived offers, or they can be long-lived. All right. Another thing that I'll get into, but offers may be denominated both either in Bitcoin and MSATs or in a fiat currency. And who thinks, or I guess, what's the reason why we would denominate an offer in fiat, for instance? Anyone have an idea? Merchants might want to, but why would they want to, right? Exactly. Yeah, fluctuations in price of Bitcoin, especially if these offers are something maybe they're weak, the expiration's in a week. Yeah, exactly. And so the offer will be, while the offer may be denominated in fiat, the payment will always be in Bitcoin. So we'll get into that. Another reason why you may want to do this is that it's kind of related, but an extension to Bolt 12, which will happen hopefully in the future, is subscriptions or reoccurring payments. And such, like if you have a subscription to Netflix, they might denominate in a certain amount in fiat, but you'll pay them every month in MSATs or Bitcoin. Yes? Yeah. It was part of the original spec, but it was we took it out initially just because it was a lot to implement, essentially. So yeah, it was scaled back a bit, but it's still on the roadmap, and I'm sure Rusty would love to talk to you more about that at some point. But yeah, it's pretty exciting to have, I guess as we go into this, we'll look at the format of the offer and how it can be extended too. So yeah, it's not like a one-time deal. It's, Bolt 12 is done, but it could be extended just like the rest of the Lightning Network has ways to extend itself with features. All right, so I think everyone understands that one. Bob has given Alice a QR code in some manner out of band. And so let's dive into the QR code. So it's encoding a BEC32 string basically here. And it is very similar to what you would see for like Bolt 11, only one difference you can see, it starts with an L and O, and that signifies this is an offer. There is a separator character and then the actual offer TLV stream. So a couple things to note, there's no checksum like most BEC32 strings, and we'll see why in a bit. And not really represented here yet, but it is, it's not signed. And we'll get into that as well as why That is not the case. And while Bolt 11 invoices are signed, Bolt 12 offers are not. And of course, like I mentioned, it contains a TLV stream. So let's see what a TLV stream is. So if anyone's worked with Lightning, you're probably already familiar with this, but TLV stands for type length value. It's a way to encode data where the type is a number. It basically is describing what the type is, so that kind of maps to something in the spec. So for instance, the amount might be a type. The length of this TLV record would be the number of bytes in it, and then the value is those number of bytes essentially that follow it. So as you're parsing a TLV stream, which is a sequence of these TLV records, you would pull out the type, figure out how much of the stream to read, and then parse it based on that type that was identified. So it's pretty straightforward. And so I'm not going to go too much into the detail here, but that's what a TLV stream is, and that's how offers and other messages within offers are encoded. All right, so I can't see this very well, so I'm going to be looking over once in a while here. So here's the offer TLV stream. So on the left side, what you see is, if you're a programmer, it's equivalent to like a class or a struct in the language. It's identifying basically the different fields within it. So each row in that table on the left are the fields in this like class or struct. We call them records though. And on the right side, it's an instance of that particular class, if you will. So here we have an offer. It could have a bunch of different fields. There's chains, so this is like mainnet, testnet, etc. There's some metadata, which we'll go into in some later slides. The currency, if you want to denominate in a particular currency. The amount, and the amount is optional, so if you want to have a donation address, you don't need the amount there. Feature bits are for extensions. We have an expiration, so when the offer is no longer valid, you will no longer get an invoice back if that time has passed. We have the blinded paths there, which I talked about earlier, and we'll jump into soon. And then some more informational fields, so like the issuer, if you want to kind of identify yourself with like a more human-readable string. Quantity is something it's in the offer spec now, but might not be as super useful to a lot of people, but you could specify the maximum number of items to purchase. So for instance, if this offer was for a cup of coffee and the max was 10, you could order up to 10 cups of coffee. Maybe it's not the most great example, but you could kind of think in the future when you think about like picking up items from a store and like scanning items on the checkout, like you buy some produce, you might enter like a quantity, so that could be useful there. But yeah, we won't talk too much about that. And then the last thing there is the node ID, and this is a potentially transient identifier, so it doesn't have to be reused. Basically, you could pick your own node ID essentially, as long as you have the signing or the private key associated with it. So we'll jump into that in a little later. All right. So that's basically what an offer is. That's how it's represented. So let's move on. One thing I guess I talked about earlier, it's not really, I guess I already went over all this, but the offer can be denominated in any currency, but eventually the invoice will be only in Bitcoin. So let's continue. All right. So now that Bob has given Alice an offer, or she obtained it somehow, Alice now wants to request an invoice so she could pay Bob. And so she constructs some message called an invoice request. And the way she sends this to Bob is she takes typically the blinded path in the offer, and she constructs something called an onion message. And this is something, as we dive deeper in, I'll explain a little more. And as the payload of that onion message would be the invoice request. And she's basically telling Bob, hey, give me back an invoice, and maybe here's some information I want in that invoice. As part of that, Alice would also include a blinded path back to her, which we call the reply path. And this allows Bob to send the invoice to her without actually knowing her node ID. Because before, the communication of the QR code or of the offer may have been through a QR code. So at that point, he may have no idea who Alice is, and he still wouldn't. All right. So let's go on and see. So this is the TLV stream. And so one thing you'll notice here is we repeat the offer in the invoice request TLV stream. And this allows for a few things. So it allows Bob, for instance, to not have to actually store the offer that he constructed. It's stateless in that sense. And that kind of ties back to the offer metadata. So Alice would also include the offer metadata as part of that TLV stream in her invoice request. And Bob would be able to sort of authenticate that that offer actually came from him, depending on how he constructs that metadata. Additionally, the payer, Alice, is including her own metadata in the invoice request. It's the first field there. Why it's the first one we'll get into in a little bit as well. And she could fill out a few things. So the chains there, if the chain is the main net, it just gets omitted basically. Like it's a way to save space in the QR code for the offer. So, but there could be multiple chains in that offer if there's like, I don't know, maybe on Liquid or something, they want to use Bolt 12. So she could specify which chain she's paying through. The amount could be omitted. So if the offer does not have an amount, there needs to be amount stated in the invoice request. If the amount or the offer does have an amount, it's either can be omitted by Alice when she constructs her invoice request, or if it's denominated in fiat, she may have to say, hey, this is the exchange rate, essentially. This is the amount of Bitcoin I'm requesting the invoice in. And at that point, Bob can verify that that's a reasonable rate before he issues the invoice. So that's why there's an amount field in the invoice request. For those two reasons, if you don't have an amount in the offer, or if the offer is fiat denominated. Similarly, there's the features bits for extensions. Quantity, so this is where Alice may say, this is the number of items I want to purchase. For many invoices, that might be just blank and there's only one item. Then we have payer ID, which is kind of equivalent to the node ID or the signing key in the offer. And as you see at the very bottom, there's actually a signature here. So this is where Alice will sign the invoice request, and she signs it using that payer ID, which can also be transient as well. It's something that she could generate and something that she could rederive by including data including any information in the metadata, the payer metadata in that field 0, or the record 0. There's a payer note, so she could add any information she wants to give to Bob. Pavs there is actually not relevant for invoice requests, but for something called refunds, which we'll get into later. And then, of course, the signature that I just mentioned. And we'll get into how that is constructed as well. It's also a Schnorr signature. So that has some great properties for anyone that wants to do like a multi-sig for signing their invoices, or invoice requests for that matter. All right. And on the right side, you see an instance of this particular invoice request. I guess their green fields are from the offer. The blue one, we have some metadata on top, and then a few later on. So I can't quite read it from this angle, but I think what I had in here is Alice actually overpaid. She gave a little bit more, and that's perfectly fine if Bob wants to accept that. And she left a message saying, keep the sat, so keep the change, basically. Yeah, so at this point, Bob is being sent an invoice request, so he can not even send an invoice back if he doesn't want to. Onion messages are unreliable, so Alice may have to request an invoice until she gets one, or Bob could send an invoice error back. And I didn't add those in the slide, but there's an invoice error message as well that he could use to send back and say, hey, I don't like this request for whatever reason, and there's some information he could fill out. Yes? There's nothing in the spec about that. No, there's a field that says like this particular TLV record in your invoice request is invalid for whatever reason, and here's a suggestion of what it should be. So maybe it's for an exchange rate, for instance. Yeah. Yeah. So we'll get into onion messages in a bit. Like you think of onion messages as a layer in the abstraction where offers is just one use case of onion messages. So the invoice error is particular to offers, but other protocols built on top of onion messages could also define their own manner of error codes. All right, let's continue on. Okay, so we're moving along now, and now Bob likes the invoice request that Alice sent him, and he sends her an invoice back on the reply path that Alice gave an invoice request on your message. And in that invoice, he included some more blinded paths, and this will contain some more information for making a payment. And I kind of completed the flow here where Alice sends the Bitcoin to Bob using those blinded paths. So let's jump into the invoice now. So very similar to the last time, we include both the offer and now I guess the invoice request TLV stream in there. And in any additional invoice fields or records. And we don't include the signature from the invoice request, but we do include the signature of the invoice. Yeah. No, so this is a Bolt 12. It's a Bolt 12 invoice that's a new format. So yeah, that's this like the whole TLV record, TLV stream idea is quite different from Bolt 11. So it is a new invoice format. All right, so we have our invoice. It has those blinded paths as I mentioned, and this blinded pay info that it gives some more information of how to make the payment. Like there's like CLTV expiries. And whatnot in there, I think like fee rates, etc. This is for the blinded portion of the payment. So, and we'll get into that in a little bit. There's some creation and expiration times. The payment hash, okay, so in Bolt 11 we had a payment hash, and now we finally have our payment hash here. And the reason why a Bolt 11 invoice wasn't reusable is because of that payment hash there. And now, so an invoice here is not reusable as well. It's just that we have the offer as a the precursor to it. There's the amount there. So this is the amount that Bob expects to be paid. And there's fallback addresses. So these are on-chain addresses in case, for whatever reason, Alice can't make the payment. Bob can offer other ways to pay. Those are optional, of course. Feature bits for extension. And then the node ID here is also assigning pub key, and it should either match the one in the offer, or it may match, which is a new spec change, a blinded node ID of one of the blinded paths. So there's a way to essentially verify it that way, or sign that way, I guess, and verify the authenticity. All right. So let's get into blinded paths. So I'm not going to get into like the nitty-gritty of like the cryptography around this, but kind of describe what it is and how it's used. So this is a key part of Bolt 12. It offers like a tremendous amount of privacy for the recipient and also I guess for the sender, because if you're sending an invoice request, the reply path is using these blinded paths as well. So the blinded path is not a full path between Alice and Bob, right? It's just a partial path. And so when Bob constructs an offer, he includes a blinded path with maybe 2 or 3 hops to him. So in the world of Bolt 11 in Lightning, typically you think of like the sender is forming the path, right? Like that still happens in Bolt 12, but for the blinded portion, that's constructed by the recipient of either the message or the payment. So in our example, Bob would construct a blinded path to himself, maybe a few hops away, and make sure there's like a reasonable amount of like possibilities that he could have chosen so that someone can infer where he is in the network, essentially. And of course, Bob might not even be an announced node, and blinded paths in that case are kind of necessary. Where in Bolt 11, you're revealing your node ID in the route hints. All right, and so this particular example shows 3 hops where the last one's the recipient, so that would be Bob. There are 2 other nodes on this path where the first one is we call the introduction node. And that one it has to be a public node, so it has to be announced. And of course, it has to support route blinding. But what would happen is Alice would essentially route her message or her payment to that introduction node and then kind of tack on the rest as part of the path that she's sending the message or payment to. And then, as with any sort of onion routing, the person who receives the message or who is handling a message on one of the hops along the way knows who gave it to them and where it goes to, but that's all they know. And so we're essentially extending onion payments to work with messaging instead of payments. There's trade-offs there, of course. Like so, in onion payments, there's liquidity issues, right? You have to have enough liquidity to send a payment through a channel. With onion messages, you don't actually even need a channel if you knew that two peers were connected in the network graph. And there's no sort of like round trip, like there's no like signing dance happening between each of the adjacent peers, and there's not like an out and back, right? When you're doing the I guess failing. So those onion messages are unreliable. It's either it gets there or it doesn't, and you don't know until you get a response, or you don't, or you retry, I suppose. Of course, that kind of brings up issues like, can you potentially DOS the network by sending a lot of onion messages? So there's ways to mitigate that. Some of them aren't quite implemented yet, but given how young this network is right now, the prevalence of support for onion messages, like it's not really a problem, but there's mechanism like kind of like back pressure to say, okay, you're sending me too many onion messages, that could kind of propagate back to kind of where you find where the problem is. So those are, I guess, areas of research that have been looked at, but it still need to be implemented, is my understanding. All right, so for sake of time, I'm gonna keep moving along. So here's that example I was saying. So we have Bob, he's kind of at the right side of the network. Alice wants to send either onion message or a payment to him using that blinded path there. It's highlighted in blue. So Alice routes to the first node there. So it's, I can't read it, it's A, B, E, I, and then so forth along the path. So yeah, so like I mentioned earlier, when a node is handling an onion message, it knows where it came from because they just delivered it to them, and it knows where to go next, but it doesn't know where it is along the path. So this, this is important for privacy, of course. All right, the time check. I think I'm got at least 15 minutes, so I'm going to keep going. So we talked about metadata earlier, and so both I guess the recipient and the payer have opportunities to include metadata in the offer or the invoice request. And this is a kind of useful way to make the implementation stateless. So I'm going to kind of run through some examples of how that would be. And there's a few different varieties of how you may construct your metadata, of course. Different implementations of Bolt 12 may do it in different ways. So here's one. So one way is that, let's say you're Bob and you're creating an offer, and the first thing you do is you generate a nonce, so a number it's only used once, it's kind of random, and from that you compute an HMAC using some secret key material that only Bob knows over that nonce and all the TLV records in your offer, except for the signing pub key, which we're going to leave out for now, and the metadata, since we're constructing the metadata. From that, we take the HMAC and we use it to derive a key pair. And the public key of that key pair would be the signing pub key. So in this construction, only that purple box in the middle, that 16 byte or 128-bit nonce is included in the metadata. So your metadata would just be 16 bytes. When that offer is given to Bob or given to Alice, and she sends invoice requests with that metadata back to Bob, Bob could look at that metadata and say, "Hey, is this an offer that I created?" And the way he would do that is he would take the TLV records of the offer portion of the TLV records in that request, and he would essentially recompute that HMAC. Using the nonce in there and the records, and then recompute the key pair, and then just check, hey, does the public key match the signing pub key that was in the offer that was given back to me? And that's a way to do a pretty straightforward way of saying, like, you could, both have a derived signing pub key that's only used once based on that nonce, and to verify it statelessly. So that's like a neat way of doing it. Some people may not want to derive a key this manner. They might want to include their own key pair. In that case, what they would do is they would take that HMAC and also include it in the metadata. So you'll have the purple and the red box there. And so now they could just basically take, and the construction that HMAC would include their signing pub key, whereas before it did not. And then from that, they could, again, verify that the HMAC could be reconstructed and verify, I guess, in a sense that that offer was indeed theirs. So another way to have the stateless offers. And then the last part of this diagram I want to point out is that for a recipient of a offer, or sorry, the person who constructed the offer, those could be stateless. But for someone paying an offer, you may want to contain some state in your invoice request. So for the payer metadata, you would use the same construction, only you could include some payer ID, and thus you could kind of keep track of, like, hey, did I already pay this invoice or this invoice request? So I sent an invoice request. If Bob sends an invoice back to Alice, how does she know she's already paid it or not? Because he could send an invoice with a new payment hash each time, right? So if he does that, Alice has this payment ID in her metadata, she could then keep track of, like, oh no, I've already received an invoice, I'm about to send a payment, I'm just going to ignore this other one. So that's a way for we're adding, I guess, 32 bytes to the metadata in that case. But that's sent over the wire, right? That's on the Lightning Network. It's not in the QR code, so that the size isn't too important there. There may be other ways to construct, like, your metadata. I think Core Lightning might do a different way with some tweak, but I'm not positive about that. But this is one mechanism. All right, any questions on that? That's probably the more technical part of this. Yep. Mm-hmm. That's true, yeah. Yeah. Yeah, the dance, the locking up liquidity and whatnot. Mm-hmm. Yeah, it's a good point. Perfect. Yeah. Could you clarify that a little? Like. Oh yeah, I mean, if you make an invoice request, you'll get an invoice back or an invoice error. No, but I think it's cheap to create one. I don't know if it's too problematic. Like, so for inbound payments, at least in the LDK implementation, I think in others, any sort of inbound payment is stateless. So we're able to reconstruct any data we need, like the pre-image to the payment hash, using data that we include in like the blinded path, for instance, like, or the payment secret in the sense of Bolt 11. So we're not too concerned about that. I don't know if that answers your question, but. It's still available, I gotcha. I'd say, like, since onion messages are unreliable, you might not get a response. There's no definitive way of saying, yes, it's still there. That said, there is an expiration, an absolute expiry in the offer. So if that has passed, then you know it's not going to be available. But yeah, but it's up to them to determine if. But yeah, but I mean, it's true that they may just not respond with an invoice. There's nothing getting around that. So if the offer still it hasn't expired, they may just not respond.
Is that just receiving the package is enough to verify, yes, this is an offer I created, yes, this is an invoice request that I received and I applied to, and then the payment matches the whole chain, right? So this is a mechanism for you to not have to remember about what you gave out as offers. Okay, thanks.
All right, we have a few more minutes so we can continue. So next I want to jump into how a invoice request and an invoice is signed in Bolt 12. So we have this concept of a Merkle tree in Bitcoin, and I think many people are familiar with that. In Bolt 12, we are essentially constructing something to sign, a hash, and we're doing it in a particular manner for a variety of reasons. So I'm going to walk through like how it's done first and kind of hopefully explain some of the rationale along the way. So this is a very small example, but you can imagine there's going to be a much larger tree. The top level are the leaves of the tree. L1, L2, and L3 represent TLV records in either the invoice request or the invoice. I'm just going to say invoice from now on to make it easier to say. And so that includes the entire TLV stream, including from the offer and the invoice request. And the interspersed elements there are nonces particular to each of those TLV records. And essentially, those represent a hash. So we'll go into how those were actually hashed. And from the top down, we're essentially saying, like, as you are moving down each level, we're having the amount of data that's hashed. So, for instance, when L1 and L1 nonce are combined, they're concatenated in a certain manner and then hashed using this tagged hash algorithm. And then the same thing happens with L2 and L2 nonce and L3 and L3 nonce. Then we're essentially left with those three blue items there. And these are essentially branches of the tree. And that continues on until, so there's an odd number there. So we're just kind of percolating the last one down one level since there's an odd number. But eventually we'll get to a root. And we'll hash that again using a tagged hash algorithm so that the message that we're assigning is specific to the context. So if anyone was in the, I think it was in the op-cat talk earlier, the cat VM talk, there was more details on how those are done. But that you could get into, like, I think it's BIP 340 or 41 describes it. And then Bolt 12 describes the exact algorithm, which the next slide will go into a little bit more information on. So this is by no means complete, but you can see some ellipses there on the slide. So the top level, there's essentially two hashing functions there. There's one for the leaf in the red on the left and one for the leaf nonce. The nonce one includes, as part of the, not the data that's being hashed, but part of the, I guess it would be part of the tag, I believe, is the first TLV record. And that, for anything that's signed, invoice request or invoice, is the payer metadata. So this is providing like payer-specific entropy to the signed message. And then we're including as part of that nonce, just the record type, which is I there. And then the leaf is somewhat similarly constructed, but we're using the entire TLV record and hashing that, and we get L1 and L1 nonce there. So, and then for the next level down, we're taking those outputs, we're putting them into our tagged hash algorithm for the branch, and it will order the items L1 and L1 nonce based on whichever's the smaller goes first. So it's comparing lexicographically, I believe, the hashes. So the order may switch as you're kind of constructing this tree. And that goes on until eventually you're down to just the root. And then there's, of course, the hash for the context. So it would be like Lightning invoice or Lightning invoice request. So there's more sort of details of like, I think it's like a double SHA-256 hash, I believe. I'd have to look that up in the spec, but it kind of describes this. And so some, like I guess, reasons maybe why we do this sort of like Merkle tree here is like, we can selectively sort of, like if you sign a message, you could eventually like selectively reveal parts of what you signed using this construction. And by having a nonce next to the TLV record, you're preventing from, I guess, like exposing the adjacent record, I believe is the reason for that. All right, I got only a couple more minutes, so I'm gonna have to keep moving. There's refunds inside of Bolt 12 as well. So a refund is essentially an offer without an invoice request, or it's an offer for money. So if you pay an offer and you want to return the item, for instance, you may want a refund for that item. So in this case, we have the same example with Bob having the offer before. Now he may be refunding the money to Alice, and so he would present a refund, which is essentially some offer records and some invoice request records, but as a QR code. And it won't be signed, just like an offer wasn't signed. And now Alice would directly send an invoice to Bob using any blinded paths that are inside that refund, and then eventually it would be paid. So there's just kind of like one step is removed from that. I think there's like a to-do in the spec about that, but that's, I think, is the reason to kind of have this similar construction with the streams, but I don't think it's fully implemented from what I remember. And I didn't put all the information in there about it, but the only difference is here is it's L and R instead of L and O. So R for refund or R for request, if you will. All right, so that's essentially like a lot of the details of Bolt 12. There's probably a lot more I could have dived into, but for sake of time, I didn't really have an opportunity. And looking at some future-facing items, so I mentioned human readable names. There's a proposal by Matt Corello for human readable names over DNS, and it also offers sort of an upgrade path from a world where you have like Bolt 12 and Bolt 11 or LN URL. Again, don't have the time to go into it, but there are some proposals out there right now, some pull requests for us in the spec. Async payments, so that's a big usability concern in Lightning now is like if the receiver is not online, they cannot receive their payment. So a way of doing this is being proposed by someone on my team, Valentine Wallace, and there's ways to do that without holding the HTLC and causing liquidity concerns on the network. So look at that for more information. And then lastly, payment notifications. This is pretty early on. I wrote a design doc based on some feedback from some companies that would like to essentially act as a point of sale in the Bolt 12 world. So imagine a merchant has a Lightning wallet, but they want to have all their inventory and all their invoicing, or not maybe invoicing, but like all their orders sort of handled by a third party, whether it's like ZapRight or Cash App, or not Cash App, sorry, like by Block, for Square. They may want to have a mechanism for the point of sale to show an offer, but have the invoice request and the invoice go to the merchant's wallet, and have the point of sale be notified of a completed payment. And what the order or the offer, if you will, it's going to be a one-time generated offer in that case, so they could sort of update all the bookkeeping for them. So that's still in the works, but hopefully this year we'll have a more solid proposal. There will be uneasy involved, but there's like some sort of there's got to be a mechanism to do that where like essentially both the merchant or the consumer can say like, here's proof of payment essentially, because we don't want to remove proof of payment from the customer. I didn't really talk much about proof of payment, unfortunately, in the talk, but a proof of payment is essentially the invoice and the pre-image to the invoice. So you have something similar in Bolt 12, only it offers as well proof of payer, so you could prove who paid, for instance, and that's done because the invoice will contain the payer ID as well. All right. So adoption, hopefully, you could begin now. You know, I guess I don't have much time to go through this, but I want to jump to this slide, I believe. So ideally, like you kind of just implement Bolt 12, both paying and receiving. But if you could at least pay Bolt 12 first, that would be ideal, or at least be the second best, I guess. And then the same with human readable names for this upgrade path. And then finally, of course, receiving as well. And then receiving from a human readable name, because you could then support other mechanisms of receiving, like LNURL, and have this upgrade path to Bolt 12 in the future. So, and then later you could always implement Bolt 12 receive. But hopefully, with implementations kind of rolling out Bolt 12 now, like this is going to become like something that's consistent, or is going to be starting to be rolled out on the network. So LDK is the project I work on, and we have an implementation out. Core Lightning has an implementation as well. Async has, I guess, Eclair has their implementation. And then I had a previous slide here, but there's something called LNDK, which is essentially another process you could run alongside LND to include support for offers. And I believe the LND team is actually working on offers as well, so they'll have full support, hopefully, I think in like 2 releases I heard, but we'll see how that goes. So 2 weeks or 2 releases. So with that, thank you. Any questions? All right, just going back there.
Early on in the presentation, you talked about recurring payments denominated in like fiat or USD.
Yep.
And my question is, what is that negotiated between the sender and receiver on like the oracle of what determines that conversion? And then the follow-up there is, does the offer during that entire time stay static with fluctuation, or does the offer need to also be updated?
So the offer would be denominated in fiat in that case, in this example, I guess. And the offer expiration time allows you to change, or if you have a shorter expiration, for instance, you could just create a new offer. But as far as the foreign exchange rates, having this oracle, as you mentioned, essentially the invoice request is sent out either with or without an amount. So let's look at the one example. Like an offer is denominated in USD, and Al sends Bob an invoice request that's blank amount. She's relying on Bob to send an invoice back that's converted to MSATs, and she could decide whether or not she pays that based on the exchange rate. Alternatively, she could propose her own exchange rate, put that in the invoice request, and when Bob looks at the invoice request, could say, hey, this is too small, or this is, and say, hey, no, I'm not going to send an invoice back, I'll send an invoice error back instead. There could potentially be. There potentially could be, I suppose, because like the invoice error could say this is why because it could say this is the amount I want actually, and I don't know if there's nothing specified about how the negotiation happens, but you could imagine that that's a possibility, I suppose.
But the offer stays static during that time.
Yeah, exactly. Yeah, you're good at the mic.
Oh, so has anybody started using these for zaps? Because I feel like you could put a Bolt 12 offer on a Nostr profile, and I feel like zaps are sort of a first killer.
Ideally,
for Bolt 12.
that would be a great use case. So if anyone in the hackathon wants to start this, that would be a nice project.
Noted.
All right, we have how many more questions? At least one in the back and one over here. I think we'll hear first.
Please.
Oh, he's asked a lot of questions. I'll let you go first. So there is MPP. Oh yeah. So for those in here, there's the question about atomic split payments. You said so. You know, there is MPP in Bolt 12, so multi-pair payment. But I think I heard described somewhere else that you could potentially have multiple payers essentially pay an invoice, right? Each one paying a part, and eventually that being. Oh, multiple receivers. It's kind of like is it Rainbow, or there's like a Prism? That's what it is, right? Yeah. I don't know if there anything prevents it, but I'm not as familiar enough with that protocol to know if it could be emulated on Bolt 12. Yeah. Yeah, with blinded paths, like I guess maybe you could do something like that. Like, are you thinking like each hop on the blinded path potentially would have like one of the recipients essentially, and they would. Yeah. Yeah, it's a good question. I don't have a good answer to it honestly, but it's something good to think about.
All right, so. Somewhere in the midst of all this, you teased the concept of one of these TLVs, the type, I don't remember what you called it, a network or a
there's a chain hash.
So
chain
right,
hash,
so
yeah.
you could support side chains. Can you expand a little bit more on that, or perhaps maybe
right now,
point us at a resource, online that talks about? For instance, I would love to see, as you said, Liquid being the obvious example.
Yeah.
And I would eventually like to see a whole mesh of elements-based side chains that can route payments like this. So.
Yeah, so the support comes at the offer level. So there's not just one chain, but multiple chains you could include there. And that's just a 32-byte chain hash, basically. So someone like Bob may say, I support mainnet, I support Liquid, and whatever other side chains potentially. And the person paying an invoice request would put which chain they want to pay on. And since Bob said he supported that in LSN, say for Liquid, then he would expect that, or she would expect the invoice coming back would be specific to Liquid. And I guess maybe it's very Bitcoin specific in the sense that, I guess.
Sure.
I guess the spec does describe as the amount being based on the network, so maybe not.
And it would allow for perhaps a list of them, so that
there
client could pick among the list and pick whichever one they already had the liquidity on or the best connection.
Yeah. So the offer allows a list, but once the invoice request is only one, so you specify which one you want to pay on. Right. Any other questions? All right, thanks for attending, everyone. Appreciate it.